be a good contribution to deep learning and AI. Next, please. So this model is basically a kind of a skeletal model of the mammalian brain. It will have sensory inputs, motor outputs, the prefrontal areas, the decision-making areas, and the three major loops: cerebellum, basal and hippocampus. It won't have 100 billion neurons because it's a reduced model. It might have about 10 billion neurons, but should capture the essential computations of all these major structures of brain. Next, please. So to this end, we have, over the last 10, 15 years, we have done some work on basal ganglia, hippocampus, next, and visual system, auditory a little bit, and eye movement, saccade generation, motor function. We didn't do anything in speech, but we did some work on bird song generation. Next, please. Then prefrontal decision-making areas and so on and so forth. So we are trying to fill the various pieces of this jigsaw puzzle and hope to assemble the whole brain model maybe in the next 5-10 years time frame. So to this end, I've divided the lab into various teams, and each team works on a specific project which dedicates itself to modeling a specific part of the brain. And as these different modules grow, we would like to assemble the whole brain model at some point. In this talk, I'm going to focus on our work on neural oscillators. Next, please. So as you know that in the brain, it's a network of neurons which communicate each other by exchanging electrical signals. Next. And these signals are in the form of these voltage spikes, which we call action potentials. Next, please. And if you look at an action potential train, which looks something like this, an interesting question that arises is, what is the neural code? What's the underlying code? How do you mathematically describe the signal in this spike trains? So there are two schools of thought, as we all know. There's a spike code, which says that information is present in the spike timings because the spike shape and size itself doesn't have much information. So you can express a series of spikes as a series of delta functions. And on the other hand, you have the rate code approach, which says that the information is present in the spike frequency. So, so these are the two schools of thought, and you will see network models and neuron models constructed based on these two philosophies. Next, please. So, next, please. So you have, if you look at the rate-coded space, there are actually not that many neuron models in the rate-coded space because you go into like artificial neural network domain. You have sigmoid neurons, ReLU neurons, or if you want to have temporal processing, sequential processing, you may want to use something like the long short-term memory block or LSTM block. Next, please. And with these kinds of neuron models, people have constructed large networks, the deep neural networks with many hidden layers. And these are the networks which are basis of this recent revolution in AI. And you're seeing the effects of this revolution in our day-to-day life. Next, please. On the other hand, if you look at spiking neuron models, and you have here also a lot of variety. The simplest kind of a spike neuron model is the leak integrated fire neuron with one variable. Or you can take the ZK-based neuron with two variables, which is very powerful. The Hodgkin model, which one of the first quantitative model of neuron with 4 variables. Or you can also have more detailed models, like biophysical models. Next, please. So here is a schematic of the leak integrated fire neuron model. It's a simply RC circuit which integrates currents and keeps on discharging. Next, please. Or the ZK-based neuron model with 2 variables. It's a very elegant model with only quadratic nonlinearity, and it can capture a wide variety of firing patterns. Next, please. The Hodgkin model with its 4 variables. Next. Or you can have very detailed biophysical models. In these kinds of models, you divide the whole neuron into small compartments and express each compartment as an electrical or electronic circuit. And you can simulate, for example, in some very detailed models, a single neuron model can be described using 500 compartments. So that's the kind of complexity that you have, even at single neuron level. Next, please. So you see that at one end, you have very artificial neuron models like the sigmoid. At the other end, you have super detailed neuron models like the biophysical models with large number of compartments. If our ultimate goal is to understand brain at the systems level, that is to understand diseases and symptoms and develop better treatments, more effective treatments based on such understanding, then obviously you cannot have very detailed models, right, on one side, or we can't have too simple neuron model because that's not biologically very plausible. what is the ideal middle ground? This is a million-dollar question, and nobody knows there's no definitive answer to that. Next slide. So here we would like to take some inspiration from engineering. How does engineering solve this problem? Because if you go to single neuron level, things get it seems to be pretty detailed and pretty low level. If you take an analogy of fluid flow, study of fluid flow in engineering, suppose you want to study the aircraft wing, you don't try to simulate the molecular collisions of the air blowing on the wing, but you invoke this abstraction called fluid, which is not single molecules but a collection of molecules, and but which is very detailed and very rigorous in its mathematical representation. We use Navier-Stokes equation to simulate such a fluid, and you can design the wing and in a finite time. So similarly, why can't we look at not a single neuron but a collection of neurons as a basic computational unit in the brain and try to develop a theory on those lines? So this is the starting point of our thinking. Next slide, please. So how do we move from a single neuron to a neural ensemble? Excuse me. So if we consider neural ensemble as a fundamental unit, what is the signal or the state of that ensemble? So if you penetrate a single neuron with a microelectrode and record it, you will see action potential trains. But if you just record from a neighborhood of a neural ensemble, then you will find a signal which looks something like what you see on this slide. And if you do low-pass filtering and remove all those sharp spikes, you will find a smooth signal, which is called a local field potential. Next slide. So once you have local field potentials and you are dealing with smooth signals, not trains of delta functions, so you can apply concepts from signal processing. You can talk about frequency bands and Fourier transforms and those kinds of concepts. So people have divided these smooth signals, especially at the level of EEG, which is a really gross kind of recording. In this, they were divided into various bands like delta, theta, alpha, beta, gamma, and these bands are given different kinds of significances in terms of what they mean in the context of brain's computations. Next slide. So now can we can we come up with a network theory, an oscillator network theory, which describes the brain phenomena at level of these high-level oscillations of neural ensembles, right? And why is it important? Can we think of this as a middle ground? Looks like that's already an important school of thought. For example, if you see this review article by Bozaki and Dragoon, which was published in Science 2004, they say that synchronous activity of oscillating networks is now viewed as a critical middle ground, linking single neuron activity to behavior. So let us now see what we can achieve at this level of middle ground in terms of oscillations. Next slide. Now oscillations are becoming popular not only in neuroscience of late, but also in computer hardware. Because if you look at the John von Neumann, who is considered the father of modern computing, way back in the 50s, he proposed that the bits and the zeros and ones, right, the bits of a computer, can be more elegantly described or represented in terms of oscillations or phases of oscillations, and not in terms of DC potentials, which is what we do in current computing technology. And he noticed that such a representation will give you more energy efficient computing hardware. For some reason, we didn't follow that line of thinking. And we have the modern computer, which is very different. Now there's no oscillations, right, really in the modern computer. But now people are harking back to von Neumann's kind of an approach and kind of reviving a whole new philosophy of oscillations-based computer hardware. There's a nice review article by Saba and Porod, published in 2019. Next slide. So there are oscillator models of neurons. I mean, it's not that we don't know any such oscillations or oscillator models. There's Wilson-Cowan model. There's Fujunova model. Next slide. Or you have Morris-Lecard model, which is actually a model of a muscle and not neuron. Then Van der Pol model has been used and pretty much, not only in neuroscience, but also in cardiology, in general physical, to model physical oscillatory phenomena and so on. Next slide. So people have used these kinds of oscillator models to represent an action potential, single action potential on one side. And also they have been used as mass models, that is like models of neural ensembles where the signal is considered to be representing the local field potential and not as the spike activity of single neurons. Next slide. So these new oscillatory models are what are called limit cycle oscillators. That is, they produce a stable oscillation with a fixed amplitude. And if you put up, and so they have a closed loop solution. And if you put up the system from that closed loop, it will come back to that same specific closed loop. And limit cycle oscillators are considered to be a good model of good approximation of brain's oscillations. Although a weak chaos would be better, but limit cycles are a decent first approach or a first cut approximation to that. And they are quite tractable. You can do a lot of interesting things with the limit cycle models. So people have used limit cycle models to describe brain's oscillations. Next. So as opposed to simple harmonic oscillator, which you had studied in your high school, right? This is mathematically very simple, but it's linear and it doesn't capture this kind of a stable amplitude property of a limit cycle. Next. So in our work, we have taken this oscillator model called the Hop oscillator, which has two variables, and the equations are given here in this slide. The equations are of cubic nonlinearity. They look a bit complicated in the Cartesian form, but if you transform them into polar form, they look actually very simple. So r dot is equal to mu r into 1 minus r squared, that is r dynamics, and theta dot is equal to 1, that's angle dynamics, so phase dynamics. If you combine these two, basically what you're looking at is a simple rotor. That is the state simply goes round and round a unit circle, right, in the anticlock direction with a fixed velocity omega, or 1 in this case. And if you perturb it off that unit circle, it will if you push it outwards or inwards, it will come back and circle towards the same unit circle. Next slide. The interesting thing is how oscillator can also be described in complex variable form using the complex variable. So they can combine the two variables x and y into a complex variable z and describe the dynamics in complex differential equation. It's a nonlinear complex differential equation. And you can easily show that the same equation can be resolved into the same either polar form or Cartesian form that I've just shown before. Next slide, please. So now the agenda that we have in front of us is, if we take this kind of an oscillator as a basic unit, a basic neuron model or neural ensemble model, can we literally rework the entire neural network theory, right, on the base of this oscillator, and then with the hope that if you apply such oscillatory models, network models, to real brain phenomena, right, they'll be able to capture brain dynamics in a more efficient fashion. So here we have done several of these things. Oscillatory Hopkin networks, we have done that. Oscillatory autoencoders, oscillatory self-organizing maps, oscillatory deep networks. So we have done this work. So I'll talk about some of these studies in this talk. Next slide. For starters, oscillators have a very interesting property. They have the property of resonance. Right? If the oscillator has certain frequency, let us say omega naught, and if you give it a sinusoidal input of frequency omega, right, when the omega naught and omega are equal, the oscillator gives you highest response in terms of amplitude. But if there's a deviation between the two frequencies, then the response amplitude goes down. And that's what is captured in this slide. And this is a very interesting property, and we'll use it at various points in this talk. Next. So that is about single oscillator. Now, how do you construct networks of oscillators? So let's start with the network of two oscillators, right? And in this case, I have two oscillators. They're coupled by the coefficients W12 and W21, right? And what can we do with them? Next slide, please. So I'm showing two cases here. In one case, the connections are positive and they are symmetric connections. So in one case, on the left side, you see symmetric connections equal to 0.5. And when you do that, the two oscillators initially have a phase difference, but just a minute, call. Hello, yeah. So the phase difference goes to 0. On the other hand, if I use a negative connection, which is symmetric, the phase difference goes to 180 degrees. So we can easily show that actually, irrespective of the actual value of the coupling coefficient, if the coefficient is positive, you'll get a zero phase difference. If the coefficient is negative, you'll get 180-degree phase difference. So which is very restrictive because we would like to have a range of phase differences and not just two values. right? So how do you achieve random phase difference, arbitrary phase difference? Next slide. So for that, we'll make use of the property that the connections are actually complex numbers. So we'll make them, make the connections complex numbers. We'll also make them complex conjugates. Then let's see what happens. Next slide, please. So you can easily show that when you do that, the angle of the connection, the coupling coefficient will be equal to the phase difference. So by simply controlling the angle of the coupling coefficient, you can get arbitrary phase difference. Next slide. So you can see this in this numerical simulation. So the angle in this case of the coupling coefficient is pi/4. And when you simulate the two oscillators, initially they have some arbitrary random phase, but after some time they settle down at phase difference of pi/4. Next slide. So that is fine, but still in this case, in the what I've just shown, the two oscillators have the same frequency, right? So that's very restrictive because brain has a whole range of frequencies going from something like 0.01 hertz to about a few hundred hertz, right? So how do you achieve a network in which the oscillators have operated different frequencies and also have some interesting phase relationships? So for that, let us start with the two oscillators with different frequencies, but quite close. The two frequencies are too close to each other. Then let's see what happens. Next slide. So in this numerical simulation, I'm starting with two oscillators with frequencies omega 1 equal to 2, omega 2 is equal to 2.2. So different but quite close. So then when the coupling coefficient epsilon is 0, then they keep oscillating at their own frequencies. But when they increase the coupling strength gradually, there's a threshold value of epsilon that you can see here. It's about 0.2, after which the two oscillators come to a common frequency. And when that happens, the originally faster oscillator will lead the slower oscillator and producing a stable phase difference. So we're able to get a phase difference, and we're able to operate with oscillators of different frequencies. But unfortunately, in the process, we destroyed the diversity. Two oscillators are firing at the same frequency, so that doesn't serve our purpose. So how do you solve this problem? Next slide. So for this, we take now two oscillators. We consider what happens if we take two oscillators of very different frequencies. Next slide. So here you see this is a fairly complicated map. For x-axis, you see the ratio of frequencies of the two oscillators. And let's focus on omega 1 by omega 2 is equal to 1. And the ratio is 1, they simply beat at the same frequency with a fixed phase difference, and there's no problem. Let us say the ratio is 1.1, like what you have seen just before, right? Where the ratio is 1.1, I need to have sufficiently strong coupling coefficient to bring the two oscillators to the same frequency. Then they synchronize. Right? The greater the deviation from that ratio of 1, right, the stronger must be the coupling strength to restore synchronization. That is around the ratio 1:1. But what if the ratio is like, let's say 2:1? Same principle applies here also. If the ratio is instead of 2:1, if it is something like 2.1, then I have to have sufficiently strong coupling strength to produce an entrainment pattern of 2:1. So if you are each of these integral ratios give you a tongue-like pattern or a leaflet-like pattern. And outside these leaflets, there's no stable phase relationship. The oscillators keep drifting across each other. So the dynamics of even a pair of oscillators, when you operate them at very different frequencies, can get very complicated. So that is what is shown in this picture of Arnold tongues. Next slide, please. So how do you solve this problem? So we encountered this when we started working on these network models, and we said we tried something different, right? So we said we cannot get, obviously, when the frequencies are different, you cannot get a stable phase difference, but we can try to get a stable normalized phase difference. What is that? That is, we divide theta 1 by omega 1 and minus theta 2 by omega 2. This difference, can we make it tend to a constant? Next slide. So for that, we used a trick called power coupling, which we have hypothesized. Next slide. So for this, imagine I have an oscillator getting input from two other oscillators. So omega 2 gets input from omega 1. So both the other oscillators feeding into omega 2. So omega 1 is sending a signal at omega 1. Right at the connection between omega 1 and omega 2, the signal is transformed instantaneously into the frequency of omega 2. Similarly, at the connection between omega 3 and omega 2, the signal is transformed instantaneously into the frequency of omega 2. So the omega 2 oscillator only gets to hear frequencies that are equal to its own frequency. So there's never any problem of lack of synchronization or entrainment. Next slide. So how do you instantaneously change the frequency? It's very simple, I mean, mathematically speaking. So you see here, you have one oscillation at omega 1. Let's say it is Z1 is equal to A1 into e power I omega 1 t. If you raise this quantity to the power omega 2 by omega 1, like shown below, it will instantaneously change to omega 2 frequency. So this is what we call power coupling. That is a kind of coupling in which you raise the variable to a certain real power. Next slide. So that's how we do it. If you now couple two oscillators in this fashion, so when I send a signal of omega 1 from Z1, that the connection between 1 and 2, it's transformed instantaneously into omega 2. Similarly, in the feedback direction, the signal coming from Z2 is instantaneously transformed into omega 2, and that's what omega 1, and that's what is sent to the first oscillator. So when you do that, let us see what happens. Next slide. So you can easily show with a little bit of math. Next slide. That the normalized phase difference between two oscillators in this case can be made to be equal to a constant, and by adjusting your coupling coefficient. Next. Just like what you've done before. And this is a simple numerical example. Next slide. So you can show that this works. And next slide. Next. Yeah, so it works very well. And we have done a lot of simulations with that. And now thing is, mathematically, it's all interesting, you might say, but biologically, how is it plausible? Here is an explanation that we can give. Now, what we are representing here is not single neurons, but two pools of neurons, right, coupled by lots of, bundle of, synapses. So in first pool, you have a bunch of neurons, both excited and inhibitory. And let us say the neurons in the left ensemble are higher, they fire at higher frequencies, and neurons in the right ensemble fire at lower frequencies. So if you take an LFP of the left ensemble, it will look like a smooth, hopefully a smooth oscillation at a higher frequency than that of the right ensemble. And at the coupling between the two, at the synapses, you can imagine, right, how by adjusting the synaptic, the membrane time constant and synaptic strengths, you can transform the higher frequency spike rates of the left ensemble into the low frequency spike rates of the right ensemble. So basically, the power coupling is describing the dynamics occurring at the level of two communicating neural ensembles. Next slide, please. So now it's fine, but how do you train the system? So I'll show you, for reasons of time, I'll speed up a little. So you can train a single oscillator and make sure how show that it can learn to tune itself to an input oscillation, as you can see in this picture. Next slide. So you can see the same thing here. Initially, the frequency of the oscillator is 40, the input frequency is 30, right? And by applying this frequency learning, it will tune its frequency to that of the input oscillation. Next slide. So now we can put together a networks of such oscillators, right? Then all the oscillators are coupled among themselves, right? Now, since you have n oscillators, you have n square coupling coefficients. And then you have forward connections called alphas. The idea now is to train this network so that it can learn any desired time series. Next slide. So this is the architecture and these are the equations. I'll skip the equations. Next slide. So in this case, we are taking a simple signal, synthetic signal, having three sinusoids at frequencies 3, 7, and 11. So initially, I'm taking about 50 oscillators to learn the signal. Initially, the frequencies are uniformly distributed, but after training the frequencies, you see that there is a chunking of frequencies. All the oscillators tend towards either 3 or 7 or 11, which are the frequencies present in the input signal. Next slide, please. So once you learn the frequencies, you also learn the coupling coefficients and the forward connections. And you see that the network can learn very well. Next slide, please. So this work is done by my PhD student Dipan Biswas. So he applied this to also EEG signals. Next slide, please. Next slide. Yeah, so I think there's a slide missing. Can you go back? Yeah. So as you can see, he's applied this to 6-channel EEG, and you can see the time series is learned pretty accurately, and even the spectrum is very accurately learned. Next slide. And we've also shown that as you increase the number of oscillators in the network, it will learn the fit more and more accurately, which is expected, because basically the network is doing some kind of a Fourier resolution of the signal, and as you have more and more oscillators, it will come up with more and greater accurate fit. Next. So next we wanted to expand this and apply this to create large scale models of brain dynamics, right? Similar to the kind of virtual brain models which can learn fMRI dynamics and MEG, EEG and all that. Next slide. So when it comes to the currently existing large scale brain models of brain dynamics, there's a little dichotomy that is being faced. If you look at the models of TVB, right, they can model brain dynamics very, very well, variety of brain dynamics, EEG and MEG and fMRI and all that, but they cannot learn behavioral or input-output functions. Right? For example, you cannot give it some visual pattern and ask it to classify, but it can learn brain dynamics. On the other hand, if you look at the current deep neural networks, they cannot learn or model brain dynamics, but they can model input-output behavior very accurately. Now, is it possible to have a modeling approach which can achieve both in a single model? Next slide. So the oscillator models that I'm showing you, I think, are capable of doing that. We have made a lot of progress in that regard. There's still a few more steps which we need to cover, but I'll show you what we've achieved so far. Next slide. So this work is done by Sayan Ghosh, my PhD student. So Sayan has taken these high-density EEG signals and tried to train the network to capture all the this high-dimensional EEG signals. Next. Only thing is, in this case, unlike the previous case, we added a hidden layer of sigmoid neurons between the oscillators and the output neurons. And with this, we're able to get very accurate approximations. Next slide. As you can see in this slide, so what you are seeing is actually the superimposed version of both the model prediction and the actual signal. You can't even see any difference. The error is of the order of 0.0 or something. Okay, now this data we got from Dr. Sujit Vijayan of Virginia Tech. This is EEG data from various sleep stages. Next slide. Next, we also applied this model to fMRI modeling of fMRI data. This work is done by Anirban, my PhD student, and we have done this as a collaboration with Bapi Raju from IIIT Hyderabad. Next slide. So next slide. So here the network is architecture is slightly different from what I've shown you before. So because in fMRI you have a separate signal coming from every region of interest or ROI. Next slide. Next slide. So for every neuron, every ROI is associated with a single oscillator and a single output unit where the ROI signal is estimated. And between the two, you have a hidden layer, a specific hidden layer for each ROI. And then the connections among the oscillators are determined by the structure connectivity matrix. Next slide. And here also we got very accurate fits. And there's a lot of results around this topic, but I think for reasons of time, I'll just pause here. And this work was recently published in scientific reports. So for details, you can refer to this paper. Next slide. Then we also applied the oscillator network and constructed a self-organizing map, and which we proposed as a model of tonotopic map. Next slide. Because maps of sounds are found in the biological world in several places. The best one example is the cochlea, where the basilar membrane acts as some kind of a Fourier transform. It computes some kind of Fourier transform the input signals. Next slide. Or if you look at the auditory cortex, the primary auditory cortices of several mammals, like for example, this picture is from bats. Right, in bat auditory cortex, primary auditory cortex, there's a very nice map of frequencies. So bats now operate using echolocation. So this particular bat operates around 60 kilohertz. So you see in its auditory cortex, you'll find the mapping from about 10 kilohertz to about 100 kilohertz over a pretty much rectilinear cortical strip. Next slide. So to model that, next slide. Next slide. So we proposed an array of oscillators And so in this array, the columns represent the frequency and the rows represent phase. Next slide. So this work again was done by Deepa, and he proposed a kind of a new learning rule to make this work. Next slide. And here, when you give a sinusoidal input of a given frequency and a given phase, a certain row gets activated in response to the frequency, and a certain column gets activated in response to the phase. Next slide. So it's a nice map of frequencies and phases, a two-dimensional map of frequencies and phases. So if you give a signal with composite frequencies, multiple frequencies, right? Then if you give two frequencies, for example, two columns will get activated for the two frequencies, and within each column, a specific local cluster of oscillators will get activated in response to the phase. Next slide. And if you give a more complex signal like EEG or something like that, it will give a very complex pattern of activation. So this is a nice model of a tonotopic map. Next slide. So similarly, we also have proposed a model of locomotion. Again, here we ventured a bit into hardware, neural hardware. This was done by Akhil and Deepan again. Next slide. So for this, we have taken a memristor model. It's a special kind of a diode, which if you put in a circuit like this with a conductance and a capacitance, this circuit produces oscillations, right? And you can easily show why this oscillates and so on. Next slide. And we have shown analogy between the phase plot of Maurice-Lécard model and the phase plot of this particular oscillator circuit. Next slide. And with this, we were able to model a variety of locomotor rhythms. Locomotor rhythms are a very interesting phenomenon in biological, movement area. So, for example, quadrupeds, right, exhibit a wide variety of locomotor rhythms based on the phase differences among the four limbs. Right, for example, walking, trotting, pace, gallop, and so on and so forth. Next slide. So by simply taking four oscillators coupled by four capacitors, and by just varying the capacitor values, right, Akhil and Deepan were able to produce various kinds of, in this case, you can see 6 different kinds of locomotor rhythms can be produced by varying those 4 parameters. Next slide, please. So finally, I come to the kind of grand challenge which we've been chasing for quite some time. That is how to construct generalized oscillator deep neural networks. That is just like you have your convolutional networks or deep neural networks in general. Can we have a deep neural network in which the hidden layers are oscillators, right? And you should be able to train the network on arbitrary time series processing problems. So we were able to do that after a lot of struggle. So in this case, I'm showing you a network in which there are alternating layers of ReLU neurons and oscillator neurons. And we have derived the learning rules for this. Next slide, please. So this work is done by Rohan and Vigneshwaran and Sayan. So they trained it using a simple input-output processing problems. So in this case, it is trained on an autoencoder. That is, the input-output signals are both the same. It learns that. It's a fairly easy problem. Next slide. Then how do you integrate a signal? If the output should be an integral of the input signal, right? It learns that very well. Then next slide. For amplitude demodulation, input is an amplitude modulated signal. Output is a demodulated signal. It learns it very well. Next slide. So now we are applying it to more complicated problems. But our ultimate goal is to realize an oscillator theory of brain function. Because I'm a big fan of Georgi Bazaki's work on brain oscillations. This is a classic that he has written called Rhythms of the Brain. So on those lines, the way it's described in this book, we would like to create an oscillator theory of various brain phenomena like spatial navigation, attention, motor function, autonomic control. We have made some progress on several of these topics, but obviously it's a tall order. It's a very large research program, but we are building small pieces in this, in collaboration with several other groups. Next slide. So basically, I think more than what we have done, I think the problem or the vision we have in front of us and where we would like to realize it with a lot of collaborators is something like this. You can make very interesting analogies between radio communications and brain communications. Because if you look at radio communications, right, it's they use electromagnetic waves for communication, but the waves used are in a very narrow range compared to the full possible range of electromagnetic waves. Right, for example, it operates in the range of 3 hertz to 3,000 gigahertz. Why is that? Because if I go to any lower frequencies, the wavelength becomes so much larger than the Earth's diameter, so the signal won't come back, right? So unless you are talking to a satellite which is tens of thousands of kilometers away. On the other hand, if you go to very large frequencies, then the loss of the signal becomes so high that the expense of transmission becomes too high. It won't be practical. So because of these constraints, you are forced to operate within that narrow range. Now, if you think of brain as an electrical medium which supports propagation of certain electrical waves, right? Then the medium will pose its own constraints, and looks like those constraints force brain to operate within the narrow range of frequencies of about maybe 0.01 hertz or 0.02 hertz to about a few hundred hertz, right? So whatever signals that it receives from the world, whatever signals it's putting out into the world, right? It must always transform the signals into this narrow range and operate within this range. Next slide. So, and also you see certain kinds of patterns of frequency distribution in the brain. Like, for example, that theta waves operate in 5 to 10 hertz, right? And cortical, higher processing of cortex, right? Or sensory perception, it operates in gamma range, which is 30 to 70 hertz and things like that. So different brain functions operate in different frequency bands. But point is, right now we keep on empirically collecting data about all these oscillative phenomena in the brain. And there's mountains of data of that kind, but there's no integral grand theory which puts all these empirical data into a simple and grand framework. So, for example, just as I leave it with a final thought, suppose that we construct an oscillative network and train it on some sensory motor function, right? What kind of frequency distributions will evolve in the network automatically? We don't put anything by hand. We'll let the network figure out what should be the ideal distribution of frequencies. And once you have that, we'll go back and compare with the brain and see if those kinds of frequency distributions are actually found in the real brain. I mean, that kind of theory would be more satisfying than trying to piece together small models which can, explain specific phenomena, and there ends the matter. They don't generalize well. I think there's a need to create a grand or integral theory of brain's oscillations, and obviously the challenges ahead of all of us. And I think that really revolutionize the way we think about brain if you can achieve that kind of a theory. And I only talked about a few baby steps in that direction. Next slide. Thank you. And these are some of the students who worked on this oscillator work. And thanks again for your patience and your time. I can take some questions. Hello.
Yes. Thank you, sir. So I'm just going to open the floor for questions right now.
Hello, can you hear me?
Yeah.
Yeah. So for that predicting that EEG waveform, what was the input? I mean, I sort of missed. What was used to predict and what was the prediction about?
So we actually took the EEG time series and trained the network. It's a generative model. We were just able to show that it can, even though it's such a high dimensional data, 64 channels, we were able to learn all the channels pretty accurately. That's all we showed. It's a simple generative model. And same thing we have done with fMRI also.
More questions? Okay. Okay, we have one more.
Follow up. So you mean to say that you can find a configuration of oscillators and connections which would reproduce the ideal that waveform when initiated?
Yeah.
Yes.
For the EEG part.
Yeah.
In case of fMRI, we took the structural connectivity data, empirical data, and so that's how the connections among oscillators are set. But the forward connections are trained so that the network produces fMRI.
Oh, I've heard this quite number of times. So,
Did that answer the question?
joking. Yes, yes, sir.
Okay, cool.
So do you want to say a little bit more about the TVB
TVB.
vision that you
Yeah,
have?
so think about TVB is it's a great modeling framework to model brain oscillations, brain dynamics, but it cannot learn input-output behavior. So for example, even a simple convolutional network, right? Of late there have been, because for a long time we thought that the CNNs are great at learning input-output behavior, but they're not great models of brain function. But of late there have been papers which showed that the CNN, the responses of hidden layers of CNN can predict the activation patterns of the brain fairly accurately, right? When the subjects are doing the same task. So that's a major kind of revelation because we never had a very high opinion of CNN as models of brain function. But the point is, in those studies, people have killed all the temporal variation and only looked at spatial distribution. So they're only looking at static data. So the dichotomy we are facing is the CNNs can capture inappropriate behavior very accurately. TVB models can capture brain dynamics accurately. Can we have the same modeling framework achieving both? And I think we are almost there. My group is almost there. I think we are now studying a couple of such problems, and hopefully in another 6 months we should be able to achieve that.
Thank you, sir. Also, I'd be interested to know your thoughts on oscillators between the brain and other systems in the body, say heart oscillations or the gut oscillations. Would you think that such models could also help us to understand the coupling between the systems as well?
Yeah, great question. In fact, we had some discussions in the lab about this. We have done some models separately to model cardiac dynamics, but actually with this new oscillator stuff, with the Hopf oscillator, I think we can couple. I talked to Anirban about this. We can couple the oscillatory brain dynamics model with a simple oscillatory model of the cardiac dynamics, and study influences in both directions. I mean, how does brain control cardiac dynamics to the autonomic system, through parasympathetic and sympathetic and all that? And similarly, how does cardiac dynamics control brain dynamics? Because when you look at fMRI dynamics, there is a huge cardiac component in that, around 1 hertz, but that's filtered away when you actually look at fMRI, which is unfortunate. But we can put it back and see exactly how cardiac dynamics influences brain dynamics. I think our modeling framework can let you do that pretty comfortably. But we need to go deeper into this and actually see what all we can study in that. And similarly with gut brain interaction also, right? We can model guts peristalsis, peristaltic movements, right, around 0.01 hertz and all that, and then couple them with brain and see what kind of interactions can be modeled. But I need to go deeper into that. I'm saying in principle it can be done.
Okay, okay. Any other questions for Professor Chakravarti? Okay, sir. Yeah, with no questions, I really want to thank you. Thanks a lot for this wonderful lecture. There have been some technical issues on our side also while presenting. The projector wasn't able to clearly showcase some of the figures, but I hope that didn't curtail anybody from getting excited with the kind of ideas you're talking about. And I'm hoping that they'll connect with you for further questions and discussions. Thanks again, sir.
Thank you very much, Pragati, and thank you everyone, and hope you have a good time with the workshop.
Thank
If you have any questions, please write to me and I'll be happy to interact. Thank you very much.
Yes, thank you. Uh, is it a break time?
Okay. Hello, hello. Can you hear? Can you hear me? Can you hear me?
Can you hear? Behave. Can you hear the voice? Mike.
Hello, hello. Can you hear me?
Sorry.
Maybe I need to move this.
Yeah, just.
Hello, hello. Can you hear me in the back? Yeah. Okay.
Speaker.
All right.
With the speakers.
Yeah, through the speaker. That's important.
Okay.
Thanks. How do I move forward? Yeah.
This forward and backward, and this is the pointer.
Okay.
Awesome.
I won't walk. I'll just lazy. Yeah. Yeah.
So there'll be a puzzle that.
Okay.
Welcome back, everybody, from the tea. We now have Dr. Pratik Mutta from IIT Gandhinagar, and he's going to present us with his recent understanding about the puzzling over interference in human motor learning. Over to you.
Yeah, thank you. Thanks, Arpan. Is he here? Yeah, Arpan is here for the invitation. It's a real pleasure to be back at NBRC after many years. As was said, but more importantly, I'm also on Twitter. We were just talking about it at the break. Somebody told me that the modern H index has nothing to do with how many citations you have, but with how many followers you have on Twitter. So my long-term hope is that I have more followers on Twitter than I have citations. So please follow me. Help me out with this. Okay, so what I will talk about is one piece that is still unpublished of a larger puzzle that we are trying to solve in the area of human motor learning and various phenomena that are associated with motor learning. And this one phenomenon that I will talk about today is called interference, and I'll explain what that means as we go along. Okay? Let me start by defining what motor learning itself is in a broader sense. So, this is kind of a fuzzy category, really, that basically involves uh, looking at how one improves one's actions under the influence of either instruction or reward or error, right? And we've done work in all three, but what I will focus on today is error-based motor learning. Okay, so the typical structure of an error-based learning paradigm looks something like this. So people start off with some baseline levels of performance, right? So these are, imagine, point-to-point reaching movements, which is what we study primarily. You're asked to move from a start position to a target, and generally people are able to do it fairly accurately. So the error in the baseline phase, which is in orange here, is close to zero. And then some kind of external perturbation is applied to the arm when it is moving, and what that does is introduce a large error in the action. Okay, and then if you leave that perturbation on, gradually people start returning back to this baseline level of performance, right? And what error-based learning paradigms typically study is that process of returning back to baseline levels of performance. Okay, this is, by the way, also called motor adaptation. What is also very commonly observed in based learning is that when that perturbation is removed, when this yellow phase ends here, people continue to exhibit the learned behavior for a while, and therefore you get these what are called after effects, okay, of learning that persist for a little while. There's interesting questions about the after effects themselves because people seem to return back to baseline behavior during the after effect phase than this return back to baseline when they are exposed to perturbations. There's hypotheses about why that is and so on and so forth. I won't be talking about the after effects as much. Okay, but if you look at whether performance has improved from baseline levels itself, the answer seems to be no. Okay, so error-based learning paradigms don't typically look at how, for example, performance limiting relationships like speed accuracy trade-offs are overcome. Okay, they're just looking at, you are knocked off of baseline using some external force or some visuomotor transformation or something like that, and how do you return back to baseline? Okay, these are over trials. Yeah, these are time trials. Um, in contrast to this, of course, is something that we call skill learning, where you start off at some baseline, but then over practice and time, you get better than baseline and you retain whatever you've learned. So learning a new sport or learning to ride a bicycle, things like that would fall into that skill learning category. Okay. Today we've done again work on that, but today we're just focused on adaptation, which is this return back to baseline performance in the face of an error. Okay. Okay, so the setup that we typically use looks like this. People who are not always bald come and sit at a table and they make these point-to-point reaching movements on this tabletop while looking into a mirror that is placed above the table. And above the mirror itself is a flat screen TV that is mounted horizontally. We are very cheap, so all this is homegrown. We get a carpenter to cut pieces of wood and we put all this together. All the software is again developed in the lab and all that. So what people see is, let's say, this green start position, and there'll be a target somewhere that they have to reach, and then we are able to display the location of the finger onto the screen in the form of a cursor, right? So if you, for example, go into one of these video game arcades, there are these games where you pick up a gun and there's ducks flying on the screen and you have to shoot them, and then you're able to move this gun around and the little dot moves. You aim that dot at at the duck and shoot. So that's precisely what this is like. Okay, so there's a sensor, or you could hold a stylus in your hand, and we map the location of that sensor or the stylus onto the screen. Okay, but what this kind of an arrangement allows us to do is fake that feedback. Okay, so because you can't directly see your arm because it's hidden under the mirror, so the mirror blocks view of the arm, right? And so what we can do is we can dissociate the motion of that cursor on the screen from the actual motion of the hand underneath the mirror. Okay, and that allows us to introduce these errors in the movement. Okay, and I'll explain one type of perturbation that we've used in that domain. Um, and then, yeah, okay. So the kind of perturbation that we have used quite a bit, and this is, we are not the only ones who've used this kind of a perturbation, is called a visuomotor rotation. So what you will see is two trajectories, right? So one is the actual hand going from this red start position to this green target, okay? And a cursor which goes off in a direction that is different from what the hand is doing, right? And again, like I said, this we can do because the cursor is dissociated, right? Because of our setup. So in this case, the cursor will go off like this by 30 degrees counterclockwise. Okay, you can do, of course, clockwise rotations and all that. So this is what the first trial would look like. I hope this plays. Okay, so just watch the hand trajectory will be in white and the cursor will go off in yellow. Okay, so um, like that, right? Okay, oops. Okay, so I'll just leave it on. Okay, so people are you need to bring the to the target. So that first trial they make these large corrections, so the hand ends up actually being quite far away from the target to make that cursor go off, go to the target. Okay, straight. And then over time or over trials, what starts to happen is people start modifying the direction in which they move their hand in order to make the cursor go straight to the target. Okay, um, and as long as you leave the cursor on, you start seeing this change in hand direction. Okay, which for us is a measure of that short-term learning. Okay, um, so you can quantify it in two ways. You can quantify it either as a change in hand direction or a change in cursor direction. They're correlated, of course. They're just offset by 30 degrees, right? So the actual data looks like this. This is a movement in the horizontal direction from the green start position to a target. This is baseline movements in which there is no perturbation. So they just go straight. And what I'm showing you is cursor trajectory. Okay, so during the first learning trial, uh, you would get the cursor going off by 30 degrees. So people correct, bring the cursor to the target. Over time, they start moving the hand off by 30 degrees so that the cursor now goes straight to the target. You've returned back to nearly baseline levels of performance. And when you remove the perturbation, remember that the hand is going this way. So now the cursor is no longer dissociated, it moves with the hand. And therefore, you get these after effects in the opposite direction as early learning. Okay. So this is standard hand trajectories. Okay. You can do this in multiple directions. People learn and you get these after effects in all directions. Okay. And like I said before, you can quantify this change in the error, okay, which is this angle relative to this straight line. Okay, the angle between the uh, start position and the position of the hand at peak velocity. So we look at peak velocity, okay, and the line that connects the start position and the target. So that's the error, and you start off at 30 degrees because that's the magnitude of the perturbation, and then over time you decrease. Okay, so this kind of learning, it becomes an elegant tool to probe certain that are going on in the brain. Okay, so what do we know about this kind of learning? One is that it seems that what you are learning is some kind of a model or internal model, as it's called, or a representation of this new mapping between how your hand moves and its visual feedback, right? So initially your map is when I move the hand straight, the cursor goes straight. And there's this new map now that you have to learn, which is if I move straight, the cursor is going off by 30 degrees. That is what you acquire and store in some ways. Okay? So there's this new properties of the environment, the body, and how these two interact. We also know, and there's pretty good evidence for this now, that there's more than one mechanism that is contributing to this kind of learning, right? And these mechanisms span various time scales. So there's these very fast acting, deliberative, what people call cognitive, explicit mechanisms, okay, that you can actually verbalize, okay, what you're doing. So in the specific case, what you would do if you were employing these deliberative strategies is you see the cursor go off to the left and you sort of deliberately uh, select an action that will make the cursor now go to the right, or your hand go to the right so that the cursor goes straight to the target. Okay, so that's one of these deliberative strategies. And then lower implicit mechanisms that you cannot really describe, okay, that also seem to contribute to this error reduction over time. Okay, like I've been saying, certain hallmark phenomena that are associated with learning. Okay, the first is interlimb transfer, which means very simply that if you adapt to this kind of a perturbation with one arm and you test the other arm by exposing it to the exact same perturbation, this other arm, the untrained arm, does not start off with the same error as the initial arm did. So the untrained arm seems to benefit from the prior learning with the other arm. Okay, so that's called interlimb transfer. This is a form of generalization. Okay, and what that suggests is when you're learning, a component of the memory that you acquired is effector independent. Okay. Second phenomenon, which is called savings, which is if you're re-exposed to the same perturbation, you're going to learn faster. Okay, so you have a memory of what you've learned before. And the third one, which focus on today is interference, which is that if you learn two opposing perturbations back to back, okay, the memories that you acquire with these two are going to interfere with each other, okay, which means that the first learning that occurred, okay, will be wiped out. You will have no memory of having learned something before if you learn something right after that, okay. So this is again shown in multiple studies, and I'll show you again our replication of some of that classic result, okay. So but yes, good question. Eye and hand, there seems to be very little generalization. But if you say, okay, I'm going to learn with the wrist and then test on the shoulder, there does seem to be quite a bit of generalization. When we test the opposing arm, it's about 50%, right? Yeah, you don't transfer completely. Okay. So the puzzle that I said that we're trying to solve is, is this, right? We're trying to ask if these different phenomena, transfer, savings, interference, tied to these specific learning mechanisms, these deliberative processes, these implicit processes, reinforcement mechanisms, use dependent plasticity, all of these, okay? Or are these phenomena simply best predicted by total learning, okay? That seems to emerge as a combination of all of these processes that you employ, or is this some other thing, okay? And what we've been able to do is provide some answers where we've been able to show that this interlimb transfer seems to be dependent on specifically these implicit mechanisms that act during learning. Okay. Saving seems to involve another mechanism, which is this, this deliberative explicit strategy use. So what is happening when you are re-exposed to the perturbation is basically that you are um, recalling the strategy that you employed to cancel the perturbation when you were first exposed to it, okay. And now, the question is, can we tie a specific mechanism to this phenomenon of interference, okay. So the paradigm that we employ, okay, so before that, if you look at what the literature suggests on why interference occurs, like anything, okay, it's a mess. But there is a classic result, okay, which is that if you learn two opposing rotations one after the other, the memory of the original rotation, or the original memory is lost upon re-exposure. Some suggest that this is a retrieval issue, which original memory is actually intact, okay, of the first rotation, but somehow the learning of the second one is impairing its retrieval, okay. That's one possibility. The second is really it's a consolidation problem, which means that these two memories are competing for the same neural resources, which means if I've learned A before and now I have to learn B, I need to wipe out A, okay. And so you're actually losing the first memory, okay, because of this dependence on the same neural resources. And what we've tried to do is, really say that, okay, if interference is because of this, okay, that you have to develop a model and seat it in the same neural sort of substrate, uh, then implicit learning, okay, which leads to the development of that model, is what should produce the interference. Whereas if it is this problem, okay, if it's a retrieval issue, then it shouldn't matter how you've learned. Interference should still occur, okay. All right. So sorry, this is a little messed up, I think. um, Translation issue. Paradigm is this, okay. So you learn a rotation A, okay. This is in this case a clockwise rotation. After that, immediately after that, you learn the opposite rotation B, which is this counterclockwise rotation. Then you're sent home and you come back 4 hours later and you're tested on A again. Now, what we did was we did ways learning B. Okay. First is the classic way, which is, you see a rotation, okay, and then you start modifying your hand direction. As you start modifying your hand direction, this, the cursor starts getting closer and closer to the target. Okay, so this is what in the little movie also. Okay, and we had 15 subjects who did this with their left or their right arms. in each. Okay, so 30 subjects total. The second way in which we induced e-learning was the following. Okay, and I'm not getting into the details here, but what we did here was not show the cursor online. Okay, so the cursor doesn't show up as you're moving to the target, but the cursor shows up at this endpoint offset, okay, by that same angle of 30 degrees, but after a delay of 2.5 seconds after you finish the movement. Okay, and it stays there for a second. This induces is strategy use. Okay, again, the reason I'm said I'm not going to get into the details is because that is a whole set of studies that has really established that if you delay feedback, okay, of the cursor, people start depending or start employing, okay, more of these deliberative cognitive strategies, okay, where they're able to verbalize what they did, okay, in order to bring this cursor back to the target. Okay, all right. So this is our way of learning be explicitly, okay, by strategies. And the third way is implicit learning only, where what again happens is that now the cursor comes back online, okay, but is clamped in a fixed direction, so it is independent of what your hand is doing. Okay? You could move your hand all over the place, this cursor is going to go this way. Okay, and people are asked to ignore the cursor, okay, and move their hand straight to the target. Okay, remember this, that people are told ignore the motion of the cursor and move your hand straight to the target. Okay, and what ends up happening though is that people actually start modifying their hand direction regardless. Okay, but the cursor never goes to the target. Okay, but the hand still changes direction. Okay, and that again has been established as a form of implicit learning. Okay, so we're able to now by these three different ways that people learn. So this has some combination of both, but this is purely strategic, this is purely implicit. Okay, so what huh, huh. Yeah, everything is in separate groups. Yes. Yeah. So the classic result we were able to replicate, of course, this we've done many times. So here is, now I'm showing you, instead of error reduction, I'm showing you a change in hand direction. Okay, so this is bins of, I believe, 4 trials or maybe 8. Okay, therefore the hand is not at 0, but if you looked at the first trial, this would be at 0. Okay, so you start off with 0-degree difference between the direction of hand motion and the direction of the target. Okay, that's what this means. And then over trials, your hand drifts up from the target to make the cursor go straight to it. Okay, this is initial learning of A. Okay, then you learn B is in the opposite direction. You the hand going the other way. But then when this is the real test, right? Which is that, okay, 24 hours later, it just overlaps with A1. Okay. Now, in contrast, if you didn't, you would remember what you learned before. And so A2, which is the green line, would start off much lower with much lower errors. Okay, this is error. I mean, I should have plotted it the same way, but anyway, you get the idea that there's much smaller error on day 2. Okay, if you don't do B, and then therefore the return to 0 error is much faster. Okay, so clearly the blue and the green here are not the same blue and the green there, right? So, which means that you've basically lost the memory of the original A. Okay, you do this with the left arm, you find the same thing. Okay, so classic result, again, adapting to opposing rotations successively results in interference between them, and the metric here is that initially learned A is not retained 24 hours later. I should speed up. Yeah, just 2 minutes. This is the delayed feedback, okay, which is the explicit learning thing. This is A learning again, B, and now there is no interference. Okay, so people remember the original A. Same thing with the left arm. Sorry. Okay. So interference does not occur if the errors induced by B are cancelled using cognitive strategies. That is, the initial learning of A is retained at 24 hours. Okay, and this is the third condition with the clamped feedback. A learning again, B, and now you get interference again. Okay, so no retention of prior A. Same thing with the left arm. Okay, so interference seems to emerge if B is learned implicitly. What we also did is look at the neural sort of basis for this by employing high definition transcranial direct current stimulation before one learns B. And this was 2 milliampere current for 20 minutes over the left posterior parietal cortex. People only use their right arm, and this was cathodal polarity. Okay. Again, I can get into the details of why P3, and why this kind of a montage and so on when we discuss later. But just trust me, there's a sort of a set of literature for targeting the posterior parietal cortex specifically. Okay. So when we do this, right, the idea is to see if you can disrupt the implicit component here. Okay, so this people are again learning in the clamped condition, which we had told you induces implicit learning only. So here you learn A, you learn B, and now you seem to, rescue the memory. It's not, it's not like the controls, but uh, who don't do the B, but it's still better. Okay, you can reduce some of the interference by messing with this implicit learning mechanisms that seem to be dependent on the posterior parietal cortex. That's the message. Okay, so disrupting PPC prior to implicit learning seems to attenuate this interference. Okay, so quick summary. We've been probing all of this interlimb transfer, interference, and savings. I told you only the interference story today because of time constraints. Interference seems to occur only when these competing memories are implicitly acquired. That is, the model of the perturbation is built. Learning an explicit strategy to cancel a perturbation-induced error does not seem to produce interference. And what this suggests is that there's some kind of a competition between these opposing rotations or these opposing models for the same neural resources. This neural resource could be the posterior parietal cortex, or for those of you who buy the network idea, some network that includes the posterior parietal cortex. Okay, and more largely, the idea is that if you understand learning and these phenomena associated with, you can start tinkering, okay, with the phenomena themselves to look at how they can be modulated and functionally exploited. I had a little bit of why we should care. There was an emphasis that we should talk about societal relevance. I'll take 1 minute to do this. So if you think about, why should anyone care about motor learning, right? This is considered to be foundation of rehab, okay? Rehab after stroke, really, or motor rehabilitation after stroke, is fundamentally predicated on the idea that people can relearn what they've lost, okay, because of that neurological injury. And in fact, if you look at what robot aided rehab paradigms are doing, and this is becoming extremely popular these days, is they often are employing these tasks in which these errors are amplified, so that when the robot forces are turned off, okay, the after effects can be normal. Okay, so if you want to get people better, right, or make their movements more normal looking, you can use robots to induce errors in their movement such that when those errors are removed, movements look normal. Okay, and so the idea is, if we understand these mechanisms that drive learning in healthy humans, we can maybe build better rehab learning paradigms. Okay, so this is the more sort of social angle to this. So there's also a more practical angle. How many of you recognize who this is? One, two. Okay. How many of you recognize who this is? Hopefully more. Okay. Okay. And I don't have to ask who this is. Although I spent 5 minutes arguing with Arpan yesterday about who this might be, and he said he was insistent that this is Novak Djokovic. Okay, so this is, by the way, is Andrew Wiles, who solved Fermat's last theorem. This is Mozart, and this is Federer, of course. So what we as neuroscientists want to understand, okay, is what is it that enables people like Federer to make highly learned, highly skilled action, okay? What is it that gets them there? And the reason I have all these three together is because we tend to associate genius, okay, with people like Andrew Wiles and Einstein and all those guys who are able to solve complex maths and physics problems, okay? But as a society, right, we at least monetarily value people who make highly skilled movements. I mean, the amount of money that Federer makes, okay, or LeBron James makes, or Sachin Tendulkar makes is ridiculous, okay? Uh, but we don't, consider these guys to be geniuses, unfortunately. You know how many people watch the football World Cup? Half the planet, okay? And it's bizarre because how do you explain, let's say aliens came from outer space, okay? How would you explain to them that half the planet is watching 22 grown men, running after a ball, right? I mean, it's just bizarre. So, uh, so this really, real societal issue, okay? Um, that we, hopefully we can make people super learners, okay, by if we understand how people normally learn. Okay, so I will stop there. Thank you very much. I'm happy to answer questions.
So particularly when you talk about this implicit learning, there is a lot of this attention distractor kind of processing also involved in that, right? So you don't, can you comment on that? You didn't really touch that for some hidden reason, but
What is attention? Sorry.
so
I,
well, by the way that I could solve the problem by suppressing I mean, if I just close my eyes.
yeah, but then how do you learn from error? It's not as simple, right? Because if you look at robot paradigms, right, there you don't show feedback, right? You could push the limb away uh, from the intended trajectory using forces, right? And people still learn. So it's not as simple as just suppression of, because then they learn from proprioceptive errors, right? Because there's some kind of expectation of the feedback that you would get if you were moving straight versus the feedback that you actually got. It's still a sensory prediction error that you can learn from. Uh, in these kinds of tasks, I don't know. I mean, I don't know what attention is doing really, or if we can. Uh, uh,
Hi. Uh, I have done this task when I visited your lab, at least a bit of it.
okay,
So,
we get everybody. Did we pay you? I don't know. Okay, sorry.
it was just us
Okay,
testing the
okay.
stuff. It was really cool. So, my question to you is the third experiment, can
Yeah.
you with confidence say that that's not implying any strategy and it's
Yeah.
solely implicit learning?
Yes.
Because probably both are there in both experiment 2 and experiment 3. And like the instruction being just to put the hand to the cursor, there is no such learning involved that I have to learn something with action. So just wondering.
So that's a good question. This has been thoroughly tested, and we have another paper that's in a preprint that has actually fully tested this, properly, whether this is really implicit. There's other groups, Richard Ivory's group at UC Berkeley, that actually introduced that clamped feedback paradigm. Okay, they've done again several studies that have confirmed this. The easiest test, for example, right? So is, I don't know how to go back here. Okay. So the paper that we have in preprint form, okay, that looks at, okay, it looks at this angular error versus this linear error here. Okay. So we call this a task error and we call this a sense prediction error. Okay. And what again has been shown is that the strategy use, okay, is driven by those task errors, okay, whereas this implicit mechanism is driven by the sensory prediction error. Okay. Now, you could argue that, look, you've clamped the cursor here, the target is here, and therefore there is a task error, and therefore strategy use must be there. Okay. The paradigm that we did was one where we said that once people start moving, we would jump this target to this location here. Okay. So the target and the cursor never miss each other. Okay. So now you've eliminated any task error that could potentially drive strategy use. Okay. Right. And people still show exactly the same behavior as they do in this. Okay. They still modify their hand path. They don't need to. Right. But they do it because that sensory prediction error is always present, right? And it seems like the system, I mean your sensory motor system, just cannot tolerate the presence of these sensory prediction errors and will attempt to cancel it even when you know you can't. Okay. But specifically to test this strategy use idea, we've done that sort of control here where we jump this onto this, doesn't matter.
Uh, so
Who is it?
can I?
Yeah.
So I had a question about those red traces that you were showing.
Yeah.
So, so two questions. If you show, yeah. So the first one is this: why is the red not starting from -20, where the blue one ended? Why is it lifted up? The second thing is that when you do the TDCS, that's right before the red one, right?
Yes.
So is there a difference between the red trace when there is no TDCS versus when there is one? It's just comparing the different.
Yeah, I mean, this is still work in progress. That's why I said this is, very little fully carefully analyzed yet. We haven't done it. Again, like I said, this is bin data. Okay, so this is 8 trials, so you very quickly learn, right? If we looked at the first trial, it would perhaps be where this ended. Okay, yeah. Again, haven't looked at it. I mean, we can see what would make most sense is to compare the two clamp conditions, right? This is the strategy and this is the clamp. Okay, so this is the right arm here, starts off here, pretty much the same. Yeah.
Nice talk, Pratik. Very nice.
Thanks.
I not surprisingly want to shift it a little bit to the speech learning domain. Okay. Again, looking at motor movements. Only there you are probably the prediction or the change that you make is based on auditory memory that you might have learned. Does something similar translate there too? That's question one. Question two, pushing the envelope a little further. When children are being taught something new, and this might, I'm pushing this beyond motor also, would you suggest based on 1 and 2 that you should rather wait to consolidate and finish learning one thing before introducing a new idea? Could that potentially interfere in their learning?
Yeah, good question. I am a little more confident about answering the second one than the first because, motor chauvinist, don't know anything about the auditory domain. What people have done though in the speech is apply perturbations to the jaw as it moves and looked at similar phenomena. It's still a form of motor learning there because it's the movement is being perturbed. There, a lot of this seems to hold, right? But feedback driven by auditory errors, I don't know much. Now, the second question is more interesting. I don't have a complete answer, but if you look at what I wrote here, okay, this bit which I didn't even mention, okay, it seems like you can also reduce interference by providing contextual cues as you learn A versus B, okay, and the kind of contextual cues that seem to work are cues that relate to your body. Okay, so for example, if I used a red target as I learn A and a blue target as I learn B, That doesn't seem to work to reduce interference. Okay, but if I learned A in one configuration of the arm and B in another configuration of the arm, it seems like you can retain both A and B even though they are successively learned. Okay, we took this one step further a long time ago, and we said that what better contextual cue than using the two arms, for learning A and B. So you learn A with your right arm, B with your left arm. There we saw massive interference. Okay, and that is related to this lateralization work that we've done before. The idea being that both, regardless of which arm you learn, you're sort of situating the learning in the same left parietal cortex. So again, I'm not fully convinced that this is the entire answer. Okay, so but based on this, it appears that you don't need to wait. Okay, before you learn things successively for them to not interfere, as long as you associate them with different contextual cues.
Thank you, Pratik. Just one final thought I wanted to know from you. What is your, I think, how would you look at explore versus exploit in this entire learning journey, especially with relevance to rehab and inducing perturbation related errors and all? Very curious.
Yeah, so I think what we need, see, this is all error driven. We are starting to play. In fact, at ACCS a few days ago, one of my students was presenting his work on modulation of implicit learning by reward. Okay, so we're starting to play with this interface of error driven and reward driven learning. Okay, in this case, again, the preprint that we have suggests that when you have an absence of reward, strategy use seems to go up. Okay, provided you create conditions where strategies can be employed, of course. Okay, if you just had pure implicit, then the strategy doesn't work. So it's really unclear, okay, of how these two interact at the moment. But what I can tell you is you can get greater net learning in an error driven paradigm if you allow strategy use when reward is not present, right? That's really the story. In terms of rehab, I think what we need to do is combine this with some kind of a reinforcement paradigm, because what we know is that even if you take robot aided rehab tasks, the after effects don't last very long at all. Okay, so just error driven learning on its own as a rehab tool is fairly useless. Okay, yeah, I'm sorry those who get offended by this, those who are interested in robot aided rehab, it has not been shown to work. So
Thank you so
thank
much,
you.
Pratik. Thanks a lot. Our next speaker is Dr. Vivek Tiwari from ISER Berhampur, and he is going to talk to us about quantifying the human brain health and disease using advanced neuroimaging and radiogenomics wrapped with artificial intelligence, a non-invasive window to sneak into gliomas and aging disorders. Oh, it's
Is it like this? Okay. Does it work now? Am I audible at the back? Okay. I'll use this. It is not working. Okay. All right. Hello, everyone. First of all, congratulations to NBRC for completing almost 25 years. And I must say that NBRC is one of the reasons for many students across country to pursue brain research, directly or indirectly. And particularly, it holds true for me as well. As a student, I think kind of like got interest in pursuing brain research by hearing that there's an institute that offers brain research course and all those things. All right. And thanks to Bhavani, Arpan, and Anindo for this opportunity. Thank you so much. So what I'll do today is I'll discuss few of our research endeavors where we are trying to understand brain health and diseases using advanced neuroimaging and radiogenomics approaches to develop a non-invasive, clinically precise window to understand gliomas, basically a brain tumor, and aging disorders like dementia. I think everyone in the audience will agree that brain is not liver, right? So if you want to study the molecular underpinnings of the brain disorders, you cannot chip out the brain at your will. You cannot get the tissue like you can get the tissue from the liver and then it regenerates thereafter. It's not true for brain, right? It's complicated, sophisticated. So doing surgical interventions is a little tricky and kind of like not everyone's cup of tea. But with the advent of genetic and epigenetic understandings for last few decades, we have several signatures, genetic signatures or epigenetic markers, which identify the disease prognosis or the diagnosis very precisely in the clinical setup, and they are being often used for the treatment decision making and all those. But the problem is you cannot chip out and you study them at the will. You need to get the biopsies. Let's say if it is a glioblastoma, a tumor, or you are studying any other brain disorder, you need to chip out the tissue, do histopathological studies, or do the PCR and all those sequencing to get what are the genetic and epigenetic features of that particular tissue or the disorder you want to study. Let's say P53, IDH, NGMT, and many other brain disorder associated genetic and epigenetic landscape. So you need tissue, you cannot avoid it. And that's I think that's one of the major challenge that why we have not been able to make a lot of progress in the clinical management of the subjects, particularly in the Indian setup where the socioeconomic background is not up to that mark to afford these neurosurgical interventions, right? And particularly it becomes more complicated when you have a disorder or a disease in the inaccessible region of the brain, let's say brainstem. So given all these complexities in my lab, what I'm trying to understand is brain disorders, particularly gliomas, aging, dementia, with the viewpoint of understanding these clinically relevant genetic and epigenetic markers. But apparently the problem remains the same, that it is invasive in the approach. So what we hypothesize that the structural changes or the vascular changes or basically the metabolic thermodynamics, which is there governing the neurometabolic pool and the kinetics, they all are in a kind of like synchrony with these genetic and epigenetic manifestations. They all go hand in hand together. And the good thing is these structural changes or the vascular changes or the function or the metabolic pool size and kinetics, you can study them non-invasively. How to do that? So thanks to Peter Mansfield and Paul Lauterbach, who gave us a very beautiful gift like this MRI so-called, which is next door in your campus. So what you need to do is you just need your head to go into the scanner and you go and sleep there, and we'll get to know what's going on in your brain structurally as well as metabolically or whatever the neurotransmitters that are there and what is their kinetics. Why? Because we as living organisms, I think we are blessed to have certain nuclei which are NMR or MR active, like hydrogen or proton, so-called, in terms of H2O or any biomolecule, glucose, glutamate, GABA, they all have protons. So you can excite them and you can study them. If you're not interested in proton, you can excite sodium, which will give you idea about the ionic balances across the cell. You can study phosphorus if you want to study more about the membrane dynamics. All right, and you can do all these by going into the scanner. And what I would do is I'll do some radio frequency manipulations. These are the RF pulses, 90, 180, 180, refocusing and excitation. I'll manipulate all these and excite your brain nuclei and get to have the structural information. So basically, if you're studying into the spatial domain, you can have the structure. By manipulating the water relaxation, you can see that there is an hyperintense part which is abnormal, and rest other parts of the brain look of the similar different contrast. We can discuss later the details if you're interested. So you can get the structure information, and if you are interested in understanding the function, so if your brain is working and if there's a stimulus, then the neurons fire. If the neurons fire, they use a lot of oxygen. So oxygen travels there. So basically the oxygenated hemoglobin, which is diamagnetic in nature, and the deoxygenated hemoglobin, which is paramagnetic in nature, creates a contrast that can be used to study the bold signal and that will tell about the neuron firing status. While you are doing the structure and the functional studies, you can also get to know what are the metabolites that are getting regulated during this whole process of functioning. So what is the turnover, what is the kinetics, or what is the pool? You can study them by exciting those chemical shifts, and you can get the chemical shift information for each metabolite or each biochemical that you are interested in. Let's say glutamate, GABA, choline, glycine, mannitol, name the molecule is there. So you can study them using the in vivo magnetic resonance spectroscopy while you are sleeping in the scanner. All right, so before I go into the details, I just want to say this very clearly that we do a lot of research in our laboratories, but apparently the amount of research being done in the labs, they're not finding space in the clinical translation, because I think if you're not dealing in the numbers, I think here is a problem. And why do I say that? That if you want to detect or identify if the person is having fever or not, you can touch the person and you can say, hey, it looks like hot or it's normal. It's a binary answer, yes or no. But apparently, do you want to give paracetamol? And what is the doses of the paracetamol that you want to give to the person? I think you can only decide because meter gives you a number. So it tells you whether it is 98.6 or 100 or 101. And once you know it is 101, okay, let's get a 1 dosage of the paracetamol. And then you follow it longitudinally over the period. If the temperature goes down, then you say, hey, this dose is worse. If the temperature remains same or rises from there, what you could do is, like, you can increase the doses of the paracetamol. So basically, it's helping you in decision making. Why? Because you are having a quantity in your hand. And this gives me a motivation that these MR images or the MR related strategies, if we start dealing them in a quantity, if you quantify them and say that this quantity says this is a normal brain with various perspectives of structure, function, or metabolic regulations, or you can say this refers to disordered brain, or this is the diseased brain, Alzheimer's or Parkinson's or FTDs, whatever. If you have a quantity in your hand from whatever the modality that you are interested, I think it's going to be more relevant in decision making. So with these discussions, I have divided my talk in two major heads. In the first part, I'll be talking about a little bit about our work on understanding gliomas, which is a brain tumor, that by looking at the structure of the tumor, can we assess what is the aggressivity of this tumor? Is it a malignant? Is it very aggressive? What is the genetic or epigenetic subtype of this tumor? And can we leverage this to understand the survival of the patient? And in the second part, I'll quickly jump onto the aging disorders, but particularly with the viewpoint of understanding the microvascular changes in the brain to quantify the brain health and the cognitive status. All right, so moving on to the first head, in 2021 and 2016, WHO revised its glioma classification, which is a brain tumor. So in addition to the histological classification, which is the conventional way in the clinics, that you identify the tumors as astrocytomas or oligoastrocytomas or oligodendrogliomas or glioblastoma based upon the histological types. Looking in the scope and you see the cell type and you can say that, hey, it looks like astrocytoma or glioblastoma. WHO said, in addition to the histology, what you need to do is you need to identify the status of the IDH gene, whether it is IDH mutant or it is IDH wild type. Similarly for the glioblastomas, whether it is IDH mutant or IDH wild type. Okay, and further ahead, like in 2021, this IDH, in addition to IDH, now they say you get to know if there is 1p19q co-deletions, then it's oligodendroglioma, and these patients are going to survive longer. They are going to have the better survival. So what I mean to say that now in the clinics, molecular markers are being introduced to understand the diagnosis and prognosis of the tumors. And particularly with the example of IDH. So IDH is one of the gene we all know from the basic biochemistry book that IDH converts isocitrate, a TCA cycle intermediate, to alpha ketoglutarate in normal condition. When there is a gain of function mutation in the IDH, IDH1 R132H, it starts converting alpha ketoglutarate to 2-hydroxyglutarate, which is not being produced in the normal cell or in any of the IDH wild type cells. So generally it's not present, but the moment you have this mutation, 2-HG is being produced. Why it is important to study IDH mutant and wild type tumors? Because over the period now it's seen, if there is a mutation in this IDH gene, these patients survive for more than 5 to 10 years. And if it is IDH wild type, the patients have very short survival spanning from 1.5 to 3 years. So if you get to know this IDH mutation status well in advance before getting the biopsy, it gives you a window period to work immediately onto the subject. design your treatment regime, and if it is IDH mutant, you don't need to worry, it's going to be a good tumor. So this was one of the questions that we wanted to address, that can we leverage the structural the heterogeneity of the tumors to understand whether it is an IDH mutant or wild type tumor. So if you see a glioma mass, it's a rendered image here. Gliomas or the brain tumors basically are very irregular in the nature. Overall geometry, if you see of a tumor, is like, you know, star shaped or amoeboid shaped. And the tumor is not only a big mass. Within the big mass of the tumor, there are various subcomponents. Like there are certain components which are called edema. Edema is like deposition of water. There are certain components within that mass which is called necrotic region, basically the cell death region. And there are certain regions of the tumor that are called as enhancing part. The enhancing part comes from the understanding that if you inject gadolinium while the person is being scanned, and wherever the blood brain barrier is leaky because of the malignant nature of the tumors, very aggressive part of the tumor, that part of the tumor takes this gadolinium and shows hyper intense spots. So you say that these are the enhancing region. Basically, these are the malignant part of the tumor. And the other parts which do not take gadolinium but are the tumor cells, they proliferate in a subtle, they are there, but they're not that aggressive like the enhancing part. So basically now a glioma mass has several subcomponents: enhancing, non-enhancing, edema, and the necrotic part. And if you see this very clearly on the MR image, you can say that you can very well say that even the subcomponents have very heterogeneous geometry. So this gives us a clue that we were not surprised if the tumors are highly heterogeneous in the nature. If you see by default the biological system per se, you will see majority of the biological systems are highly irregular in structure. If you see a cancellous bone structure or molar shell or even the floral patterns, they are highly irregular. And the moment the structures are irregular, you cannot use Euclidean geometry to study them. And not to be surprised, even Mendel found out that from the pea pod, not all the seeds are round, some of them are wrinkled, which are very heterogeneous. And if they are wrinkled and if they are round, it is being governed by a factor that they carry, whether it is RR or it is a, like, you know, small r, small r. So basically there is a factor which is governing the phenotype of these manifestations. So similarly, what we hypothesize is that by quantifying the geometry or understanding the phenotypic manifestations of these subcomponents, we may be able to understand whether the tumor is IDH mutant, wild type, or per se other mutation that you are interested in. So as I told, these are irregular structures, and to measure the irregular structures, you need a fractal geometry, because if there's a line, then this is a non-Euclidean geometry. Basically, you can it's a Euclidean geometry. You can cut the line in two parts and then you put them together, you get one line, right? But for the irregular structure, you cannot use such kind of dimensions. So you need to have something called as fractal dimensions, and fractality will tell you about how many self-replicating structures are needed to complete the whole geometry. So what we intended to do was to measure the fractal geometry and another dimension which is called lacunarity, which measures the gap in the structure. So the structure, if it's not continuous, there are gaps, you can quantify them by using the lacunarity measures. So I'll discuss about the fractality part here, that we had these tumors from TCIA and various Indian sites. We club all of them and we developed a pipeline in our group to first of all segment these brain tumors across these enhancing component, non-enhancing component, and the edema component. And you have tumors which are identified by biopsy, IDH mutant and IDH wild type. So we determined the fractality and the lacunarity across all these subcomponents for almost 213 subjects. Okay? And what we see, if you have the enhancing component and if you measure the fractal measures for the wild type and the mutant, and you see the median or the mean of the fractal dimension for the enhancing component for the IDH wild type is way higher than that of the mutants. And I told that if the fractality is high, it means the structure is highly irregular. So what you see for the IDH mutant, which are the better survivals, for them the enhancing component geometry is very homogeneous. They're not heterogeneous into the by nature. Whereas the IDH wild type, which provides a poor survival, poor prognosis, they're highly irregular. So enhancement is kind of like, you know, encompassing the whole brain, and they're very irregular into the nature. But if you look at the non-enhancing component, which is basically a slow growing part of the tumor, and if you see between the mutant and the wild type, the mutant shows a high regularity compared to the IDH wild type. Whereas if you see for the edema component, basically which is a water deposition, not per se a cellular structure, you don't see any difference between IDH mutant and wild type. All right, so we had these numbers in our hand what we did, we trained a model, and we did SVM, KNN, and the random forest training of this model by using the fractal and linearity measurements. And what we see, if you have an enhancing component FD and the non-enhancing component FD, basically fractal dimension, you put them into these models and you see these blues, which are the wild types, and the reds, which are the mutants, they get very well separated in the space. And the accuracy of our prediction to quantify whether it is an IDH mutant or wild type based on the fractal dimension is almost 90%, given the number of the data that we have right now. And KNNs and random forest, they're also not performing that bad. So basically, what we are at this stage now, that you can identify whether the tumor is an IDH mutant or wild type with a 90% accuracy if you have the fractal dimensions of each subcomponent. But basically, the optimal combination of using both enhancing and non-enhancing subcomponent provides you a very high accuracy. And this can also be seen here in the AOC curve analysis, that almost 92% accuracy and sensitivity is seen here when you are using the SVM model to predict the IDH mutant and wild type based upon the fractal measurement. Okay, what we did for all the subjects, we use a log rank statistics and find out a cutoff value of for all the components, basically the enhancing, non-enhancing, and the edema subcomponent, and try to see, does this FD measures give any idea about the survival of the patients. So if you have an FD of more than 0.69 for the enhancing component, you see this comes with a poor survival of the patient. Whereas the FD, which is the measure of the irregularity, if it is less than 0.69, so less FD, less irregularity, they have overall better survival than components having FD more than 0.69. Similarly, for the non-enhancing component, if you see the fractal dimension, if it is more than 1.2, basically you are having a better survival, which is almost reverse of the enhancing part. And if the FD is less than 1.2, they come with a poor survival, whereas you don't see any difference coming from the edema component. Okay, so this was for the structure part, because when I talk to clinicians, it's very easy for them to deal with the structure, deal with the MR image. It's being done almost every radiological sites across India or anywhere, and it's easy for them. But as I told, that there is a very unique function associated with IDH mutant tumors, that they start converting alpha ketoglutarate to 2-hydroxyglutarate, which is a metabolic reprogramming associated with IDH mutant tumors. You don't see anywhere else. And this comes from a very nice study in Boston in 2009, where they were sequencing a group of gliomas, and they found that the IDH mutant tumors produce 2Hg by orders of magnitude. When I say orders of magnitude, means it increases from nanomole to the millimoles. And if you can quantify this 2Hg, I think it becomes one of the first metabolic signature to tell whether the tumor is IDH mutant or wild. And indeed, I'm actually very much interested to develop the MR strategies to detect these biomolecules. But the problem across the globe right now is, if you use the conventional spectroscopic method available on the scanner, which is called a short T spectroscopy, if you use that, and let's say I'm showing here a healthy example, that if you place the voxel in the medial occipital region and do the conventional short T spectroscopy, you get these kind of metabolites like NAA, which is well known, still aspartate, which is a neuronal viability and density marker, creatine, choline. Choline is a the cell proliferation marker, creatine related with some energy metabolisms. But when as a neuroscientist or neurooncologist, you tend to understand GABA or glycine or glutamine or glutathione, lactate, I think it's not easy to detect with a short T spectroscopy, because of the inherent problem of the spectrum, that there is a lot of spectral overlap, and you cannot distinguish them if the concentration is low and if they are having the multiplets. So they are kind of lost. Everybody is having overlap with other signal. So it's hard to detect with the conventional spectroscopy. So this was my interest, that I wanted to detect 2-hydroxyglutarate in the tumors using spectroscopy, so that just by looking at the metabolite, if I can comment whether the tumor is an IDH mutant or wild type. So this is the spectra acquired using the conventional scan, which is a short T 30 millisecond scan from this IDH mutant tumors, which was confirmed after biopsy. You see here, this is 2Hg, this is glutamine. You can say something. If you give an input, the scanner will give you some output. But whether that output is clinically precise to comment, no. Because if you see the CRLB, uncertainty in the estimation is pretty high. And the moment there is uncertainty, I think better not to take it to the clinics, because when you are saying something in a clinical setup, it has to be precise. So I was interested and to develop a method to better quantify these 2-hydroxyglutarate and other metabolites as well. I'll not go much into the details, but if you use the basic NMR strategy or the understanding of J coupling, you can tailor the spectroscopic profile. If the peak is upright, you can make it inverse. If the peak is multiplate, you can tailor it so that there is not much spectral overlap. I'll just quickly show here that if this is an A and you have a CS3 here, which gives a signal here in this green form, and if you have CS2 and CH, basically H and H, they are both NMR active, they are side by side, so they will affect each other's via a phenomenon called J coupling. And I don't know, can I play this? So just for understanding of the students, if you vary the timing of the acquisition, the echo time, you see here that this green is going down, whereas if you see these blues which are coming from these coupled signals CS2 and CH, you can see that you can vary signal strength and the pattern both. Whereas for the green, it just goes down. So this gives us a clue. I mean, take my words, and if you're interested, we can discuss it, that by manipulating these timings, you can play with the signal strength and the pattern. So I use this strategy to actually tailor in vivo mRNA sequence so that we can identify 2-hydroxyglutarate. We did it, and we have a method called a press T 97 millisecond that allows you to detect these 2-hydroxyglutarate with clinical precision, and you can quantify 2Hg. So this is an example. This scan was obtained at NIMHANS. I trained people there and established my sequence at NIMHANS scanner. You put the voxel here in the tumor and you can quantify 2-hydroxyglutarate here. So 2-hydroxyglutarate is estimated around 5.6 millimolar, and I am blinded for these mutational status. So I say to the clinician that you give me the, I acquire the spectra, you give me the spectra, I quantify it in my lab. You don't tell me what is the molecular status, I will predict it, and let's see, do I have confidence to predict whether it is an IDH mutant or wild type based upon the 2-hydroxyglutarate quantification. All right. I also established, I'm working across various clinical sites. So this is one coming from a SAM hospital in Bhubaneswar, where I've established this sequence, and we are still, it's working well. We need more data though, but this is 2Hg scan, not that great. There's a lot of spline here, but 2Hg is being detected here, almost 3.6 millimolar. And again, based upon, if 2Hg is being produced by default, you can say it is an IDH mutant tumor. So I'll skip this part. So what I have to offer now to the WHO classification system and in the clinical translation, that you can quantify 2-hydroxyglutarate. You don't need the tissue to identify whether the tumor is IDH mutant or wild type, to say whether the subject is going to survive long or not, whether the subject needs an alkylating agent based chemotherapy or not. For that, you don't need tissue. You can quantify 2-hydroxyglutarate, and you can say whether the tumor is IDH mutant or wild type. In addition to that, to make it more reliable for the clinicians, because you don't, there is, for the spectroscopy data, you need some hand massaging, some expertise. But if you have imaging data which is readily available and you can train it, so now with the fractal measures that is having geometry and 2Hg, if you have these two together, I think it's the black box of the tumors is no more a black box. We do see some white thing there, and we can comment on the genetic status by quantifying at least these two, 2Hg and geometry, fractal geometry for identifying IDH mutant and wild type. Okay, I'll skip this in the interest of time. So we are also doing a lot of RNA-seq analysis to see why these IDH mutant tumors are responding well to the treatment. What are those genetic advantages does it carry if it is an IDH mutant? So we are having certain markers. This is just one quick story that's developing in my group, that the IDH mutant tumors have increased expression of the certain solute carrier transporters which allow uptake of the chemotherapy agents. So basically, there's a lot of expression of these. So as a consequence, if the TMZ is delivered, then the IDH mutant tumors take up these TMZs very efficiently compared to the IDH wild type, and that's the reason that why these IDH mutant tumors respond well to the treatment, and many more things. And recently, I got a SERV grant to actually study this. What is the underpinning of these 2-hydroxyglutarate? Why an IDH mutant tumor is responding well to the treatment? What are the metabolic reprogramming or the other landscape that makes it a good tumor, not a bad tumor like IDH wild type? So I'm trying to study what are the sources it uses, and does it help in the cell proliferation, or how does it deal with the hypoxia? It's all coming up. We have developed in our group actually several wild type and the mutant cell lines in UAT7 and LN229 to study these molecular markers. So in nutshell, the whole aim is that if you go to a cloth shop and you touch the cloth, you can say the texture of the cloth, whether it is a cotton or silk or mixture of the cotton silk, or what kind of like cloth is it? So similarly, if you can use these MR images and tailor your method to understand the texture, pattern, metabolism, and all those kinetics together, and say what kind of the what is the genotypic or the epigenetic landscape of this tumor, and can we leverage this in the clinics for the betterment of the patient. So this is one perspective that we are actually continuously working on. So now I'll change the quick gear, move on to the aging and dementia part, and it will be quick wrap up. I do have time. 5 minutes, yeah, perfect. So I'll not go to the details which Neha talked about yesterday for understanding the anatomic volumetry, to understand the sequence and the magnitude of brain-related changes with aging and dementia. But I'll share something, some interesting finding that we are having in our group, that if you see a human brain above 45, I mean, I don't have data below 45, majority of them tend to have something called an abnormal structure aberration in the brain, which is called white matter hyperintensity, which is basically a small vessel disease, so-called disease. But I won't, since I'm looking these images and they are classified as cognitively normal as well. So I don't know, I don't want to say the term disease, but there are certain small vessel aberrations which are being seen almost in majority of the patients. So if you have data about 50 to 64 or 65 to 79 or 80-year subjects, majority of, like, almost 54% have WMH, whereas the other subset do not have WMH. So and they are being classified as cognitively normal. So that's again a problem, that you deliver a cognitive battery, but you are not able to see whether there is a structural aberration in the brain. You may have wound on your skin, but it may not give you pain, but it doesn't qualify that you don't have a wound. If there is a wound, it means brain health or your structure is not actually normal. But just by doing the cognitive battery, you say the person is behaving normal or have normal cognition. I think we need to have a debate on that. So if you see these white matter hyperintensities, you see there are certain hyperintense spots here near the ventricles. So these are called as a periventricular white matter hyperintensity. Some of the white matter hyperintensities are seen also in the deep brain structure, which are called as deep brain white matter hyperintensity. So it's pretty abrupt around the ventricles and in the deep white matter. But these are very different from the multiple sclerotic spots. Okay, these are very symmetric, unlike the MS spots. So we wanted to understand that why few people deposit it, few do not, and even those who have it, they have distinct magnitude of these WMH, and does it have any implications on the brain structure health or the cognition of the subject. Okay, so if you see here, this is periventricular and this is deep white matter. We had data of cognitively normal, impaired, and the Alzheimer's disease subject. And if you make the probabilistic map of the deposition of these WMH across these groups, you see here in the early age group, yeah, across, like, even for the normal, you see a few spots, but the progression increases, and you see more blues here going for the higher WMH load. If you look for the impaired MCI subjects, you see here more reds now coming in at the late age. You see more WMS there. For the ADs, even you start seeing at the intermediate age that the deposition is increasing here for the periventricular, and similarly for the deep white matter. But unlike PV, you see almost pretty less in the early age group, and with progression also you don't see somehow more deep white matters in the normal and the MCI, but I do see lot in the AD cases. Okay, so we wanted to understand that why some are having periventricular white matter hyperintensity, some are having deep white matter, and some are having both. And if having both, PV is higher, DW is low. What does it mean? So we wanted to begin the study and understand the kinetics of this progression. And if you plot the progression of the periventricular and the deep white matter, you see that the deposition of the white matter hyperintensity in the periventricular region deposits much faster compared to the deep white matters in the cognitively normal subject. For the impaired subjects and the Alzheimer's disease, you see the deposition of the periventricular again is faster, but again the deep white matter also picks it up. So basically, you see here they begin at a very low level in the normal subjects, but in the impaired and the dementia, even at the 50-year-old, the graph begins pretty high, and the subject having periventricular high load of periventricular at this given age of the early 50 years also. So basically, this gave us a clue that periventricular and deep white matter, they do not follow a similar kinetics. They are having distinct kinetics, and the deposition across periventricular is having a different phenomenon than the deep white matter. If you quantify them, and we developed a segmentation method in our group to understand this periventricular and deep white matter, you see here the periventricular white matter hyperintensity in the MCI and AD. If you have an early age group, MCI and CN, they have more or less, if you see all the population, more or less similar WMH load at the early age, but the dementia, basically the AD group has a high WMH load compared to MCI and CN both. And here it's around 2 ml. It increases with age, right? So now 2 becomes 10, 10 becomes 20 now. So it's going exponentially high. So the scale is different here. You can see that. So basically the progression is happening across all three, but the increase in the MCI and AD is kind of like similar at the other age groups. MCI and AD cannot be distinguished from the CNs. Okay, so I'll quickly skip this part. So we further went on to the deep white matter, because deep white matter, when you say it's parietal, temporal, and everywhere. So we went on to each region and segmented these white matter apparent densities. And I don't know, this is very intriguing for us. I don't have explanation for it. For MCIs, what we see that even at the early age group, if you study frontal and the temporal, they have huge white matter apparent density compared to the CN and AD. And I don't see such differences in the parietal and occipital lobes. So we further went on and did some cognitive assessments and wanted to understand whether these WMH have direct effect on the cognition or it is mediated via the structural changes. So we did a mediation model analysis, and what we see that almost 52% of the effect on the cognitive test like trail making test, which is basically an executive function memory test where you have a score, you have to perform a test within a given duration of time. What you see that the periventricular WMH load is responsible for impaired trail making test score, almost, which is mediated directly via 52%, whereas 48% comes via the structural changes in the paracentral thickness and rostral medial frontal volumes and the lingual thickness. They contribute around 48% for the subjects who are having poor performance in the trail making test P. So I'll skip this part, and we are also developing several MRS methods to distinguish gray matter, white matter, and white matter hyperdensity metabolic differences. We have established this method to separate glutamate, glutamine, and NAG at 3 Tesla, and you can see that the NAG, I don't know, I don't have explanation for it. It's low in the gray matter part, but it's very high in the white matter part. I don't know what happens in the white matter hyperdensity. We are on to that. So yeah, with this I will skip this. And the major aim of my laboratory in the aging part is to combine multimodal and multivariates to develop an AI ML based model to predict the brain health and the brain age, so that we can contribute to the society in early identification of the trajectory of the aging subjects. And thanks to TCIA and TCGA and NACC ADNI for the aging and the cancer data. And my collaborators are Sri Chitra, Manoranjan at KIMS Bhubaneswar, Sani at NIMHANS, and Garg at AIMS Delhi, NMR group, and my students. Thank you so much. And let me say, I mean, this place, NBRC, has always been in news for doing very tremendous work in understanding aging and dementia, from identifying those glutathione in the brain via Professor Mandal's research. So that's also something that you all are not unaware of. The spectroscopy technique is there, and it's giving information to understand these brain disorders. Thank you.
Thank you, Vic. That was really exciting neuroimaging work. We really don't have time. Is it okay to have all questions during the discussion?
I will love that.
Yeah.
No
Okay, we
problem.
have a small announcement.
So I think one of the senior scientists from DBT, Dr. Gulshan Wadhwa, is going to talk about brain and leadership. So we had him scheduled at 12:45, but because of the delay, so we are running late. But I think he's here. Let me see. Can you see? So thank you, Vivek. So Dr. Wadhwa, can you? Okay. Dr. Wadhwa, can you hear me?
Yes, I can hear you.
So maybe you can turn on your camera so that I think the audience can see you. I think you can see the audience probably. Can you turn on the camera also?
Camera is on.
Okay. So you can see the audience?
Yes.
Okay, good. So we can't see you yet.
Why?
So else you can share the slides if there is a problem with the camera.
Yeah. Sure.
So we are all very thankful to DBT for supporting this event, and
Welcome, sir.
forward.
DBT.
Yeah, we look forward to your support in future also. Yeah.
Yeah.
Okay, your slides is about to, yeah, we can see your slides. You can go to the full screen mode.
Yeah, that is what I'm trying. Yeah, can you see it now?
Yes, the full screen is not still visible. It's still in the slide view mode.
It's on my side, it's showing full screen. Maybe I share again.
I think there's a lag. Maybe it will come up in few seconds or
Now,
not yet.
I stop and again do it.
No, no. Now the slide is gone completely.
Yeah, I have removed it. I'll share it again. Do I have to make it full screen beforehand? No, so hold on.
Yeah. So I think yeah, I think he's trying to do that. For so you can try on the right hand corner the presentation, that
That is
symbol.
what it's on my screen. It is showing full screen.
Hmm. So can you try function F5 once if you on your keyboard?
F5,
F5.
F5 and 1 together.
Function and F5 together.
F5 and 1 together.
Else it's okay. It's fairly big. We can work with this, I think.
So all of you must be discussing about brain and learning about brain. The structure, the function, the other details and all. Today I'll be talking with you about the brain and leadership. What a leadership require brain to do and what brain can do for the leadership. The brain is just a complex organ that controls thought, memory, emotion, touch, motor skills, vision, breathing, and body temperature, hunger, and every process that regulates our body. Together, the brain and spinal cord that extend from it to make up the central nervous system or CNS. All of you know this. Some basics: the brain is the most complex part of the human body. This 3-pound organ is a seat of intelligence, interpreter of the senses, initiator of the body movement, and controller of behavior as well. So it is a crown jewel of the human body as it is known. The fact sheet and the basic introduction given above about the human brain, it helps us to understand how the healthy brain works and how to keep your brain healthy and what happens when the brain doesn't work like it should work. Are the slides changing there? So the brain has 3 components, structure and all. I will not discuss.
We
I'll
don't.
simply
Hi. The slides are not changing.
okay, how to change them.
Do you want to try changing the slides right now?
Yeah, it will be better. Is it
Yeah.
changing?
Right now we see it changing.
But then again, it's not in full screen mode.
Yeah, it is okay without full screen. We are able to see your slides. Now we are able to see it change as well.
Yeah. Maybe I'll run in this mode only. You have on the screen, you will be able to see it, most of it.
Okay.
So, brain, all of you know, I need not describe. Geography of the thought is here. Frontal lobe, parietal lobe, temporal lobe, and occipital lobe and cerebrum. They control different functions, which I will not be reading out from the slides. So I'll simply pass on the slides. Then motor cortex, sensory cortex, the inner brain, the neuron, the synapse, and some key neurotransmitters. all of this you know. I need not describe it once again. So the aim here is how to maximize the capacity of the brain, or the real potential of the brain, or the real potential of the team, in other words. The brain is a source of who we are, what we do, and how we do it. Objectives of my presentation is to indicate the emerging knowledge of the brain and relate it to to its potential and team leadership. Use the knowledge of the brain to understand why uh, project execution or thought process or the leadership uh, emerges, and why it is not emerging in all the people. Why only some people are able to do it? Why not all the people? So I'll be presenting a brain-friendly idea related to the project execution and team leadership. The brain and leadership. There are 6 major challenges in executing the project plan or the thinking process. First one out of this is neuroscience of distrust, where higher level of cortisol shut down the prefrontal cortex and our ability to think empathetically and with good judgment. Amyloid Gadala activated to fight or flight. Networks turned on. So either we fight with a system or to achieve our aims, or to run away from it. And higher levels of testosterone and norepinephrine with heightened aggressiveness and negativity also play a role. Neuroscience of trust, that means feeling trust and releases feeling the trust releases the dopamine, which gives us feeling of optimism, positivity, feeling good and excitement. So we feel happy, we feel willing to work, and then again oxytocin, which help us to feel closer to others and a desire to want to collaborate with them. Serotonin is the third chemical which helps us to make us feel good. So these all expressions by these chemicals are expressed mainly on our face and in our actions, which lead us to take different actions and finally lead the people in the process of our thought, and make them follow your thoughts by convincing them and by taking them together as a teamwork. Negativity is one workplace is another factor. Negativity bias in organizations or the individuals is a phenomena by which humans pay more attention to and give more weight to the negative rather than positive experience or other kinds of information. So we have to change from negative thought to positive thought to bring in the leadership. There are 5 times more negative networks than positive networks in the brain. So in other words, we have to put at least 5 times or more effort to bring in or bring in front or use the positive thoughts in the brain, and therefore the leadership is comparatively a tough job. Not all people can do it, and not all individuals, not all organizations can do it. Then the third factor in this is impact on work culture is devastating. The impact of negativity on the work cultures of individual and the organization is devastating, and it leads to harm to the organization and individuals. Then we have rational versus emotional brain. Most managers tend to focus on the rational thinking rather, while ignoring the role of emotion in the behavior of their employees and customer. But if we also keep into account the emotion of individuals, it will be very helpful to them as well as the organization to grow and grow faster. In implementing a project plan, emotions play a critical role because emotions give you a thrust to progress and to lead. There are 3 cognitive biases in planning using the brain. One is the accountability bias. We believe that we can control outcomes more than it actually the case is, resulting in poor risk assessment. That means overemphasis, and similarly the status quo bias. We prefer the status quo in the absence of pressure to change it. So leadership requires a change. Present bias, we value immediate rewards and undervalue long-term gains. Most of the time we are not able to judge the long-term gains. We are not able to foresee the long-term gain. So we just see the immediate rewards and just take the immediate reward and be happy with them. And long-term goals and gains are left in the process. There are 9 other common cognitive biases which are also involved in the process. Then, of course, environmental triggers are one major factor. Environmental triggers, any stimulus that reshapes our thought and actions, means it will affect the different parts of the brain, and brain will be activated in a very, very different way. Our environment is a non-stop triggering mechanism whose impact is too significant to be ignored. It seems that the brain was designed to allow us to effectively plan, but not adequately cope up with the inevitable change that will occur as we implement our plans. So change will always occur, but we are not ready to accept. So our progress is hampered because of that. Brain sees change as a threat. Tomorrow, if somebody comes and tell me, okay, you shift to that smaller room and sit there, what will happen? My brain will not accept. If they see that you are given a different work than what you are doing, brain is not easily able to accept all this. So the brain's error detection system, when the change occurs, the brain generates error detection signal as a result of new incoming stimuli that conflict with existing mental maps. So whatever we have mapped over a period of time, that remains as a memory, and that our brain thinks that system will go only in that direction. There no new things will come in to bring in a change. So we have to be very, very careful to observe the change and accept it, to become a leader, to lead the people, and to contribute to the leadership. In summary, low levels of trust, toxic work cultures, failing to account for the emotional natures of the brain's cognitive mental biases, environmental triggers, the brain sees a change as a threat. These factors affect the leadership, and we have to overcome all of these to take the work to a conclusion and lead the people and lead the organization. So there are solutions to it. I'll be discussing about 2 solutions. One is the whole brain thinking. So you use your whole brain to leverage your thinking. Don't allow the different parts to see different things. I will give you an experiment. All of you in the hall, do you have some paper with you? Do you have a sheet of paper with you? You acquire a sheet of the paper. At the end of my presentation, I will be sharing with you something which will tell your brain different things than what you actually see. Are you ready to do this experiment, all of you?
Yeah. Yes, we do have
So
a
please
piece of paper.
collect a sheet of paper, and at the end of the presentation, we will see how we can create a hole in our head. That will tell us how brain sees and how brain perceives. So different tasks and problems require different mental processes, and the way people prefer to think influences how they process the information, how they tackle the projects, how they interact with others, and how they view the opportunities. Different people think in different ways, so all these things change. So for a leader to act as a leader, you have to have all this overcome all these 6 factors which I have discussed previously, and this will help the brain and help the individual and help the organization to grow fast and lead the area. So each of these different thinking preferences bring unique value to our work and culture. The whole brain model is shown here. 4 components: cerebral mode, the right mode, the limbic mode, and the left mode. You can see the logical uh, analytical in fact-based and quantitative. This comes under the A part, and organized sequential plan and detailed work comes under the B plan, where left and limbic mode are working together. The holistic, intuitive, integrative, and synthesizing kind of thoughts come under the cerebral and right mode, and interpersonal, feeling-based, kinesthetic, and emotional thought comes under the C part, where limbic and right mode work together. So all these things should work together, all parts of the brain, so that we can have a thought process which will help us to accept the change and bring the change what we want to see in the things around and our projects and other places, and lead the become a leader. So think about communicating. The upper left parts or the A parts tells us the critical analysis of the facts, no fluff, technical accuracy, goal and objectives, well articulated ideas, data, facts-based charts, brief, clear and precise information. Similarly, the lower left part shares with us, tells us to do detailed time action plan, thought with the references, rules and procedures, step by step, concise in writing and in advance contingency plan, so that no digression is there. Upper right part, the yellow part shows us the minimal detail, the freedom to explore metaphors, visual overview, and the big picture, new and fun and imaginative and conceptual framework. This aligns with the long-term strategy. So this part we have to use for the long-term strategy, apparently, which most of us do not use, including myself. So the lower left part, which is shown in the red, indicates the open informal discussion, expressive body and voice, intros and introductions and conversations, knows the effect on the others, knows the how people feel, hear and understand, and there are no hidden agendas in this. So this fourth or the C part is the most crucial part, which helps us to take to the leadership. Developing a strategic plan for the whole body, whole brain way. So we have to define the goals. We have to gather the facts, analyze the information, clear understanding of the relevant fact, financial consideration. Financial consideration we do in writing the project, but not in research paper writing. Similarly, we have to understand the technical aspects and analyzing the impact of future on today's decisions. Similarly, in part B, we have to break the big picture into the key initial points, or we have to know the steps by which we have to reach the goal, then putting together a sequential set of actions, steps in the form of a plan, thinking through the consequences of approaches we follow, administration and organization of the plan, implementation, follow-up, evaluation. Similarly, the in the yellow part, you can see it helps us to for risk taking, relentless pursuit of opportunities, seeing into the future, perceiving the possibilities, making connections and synthesizing insights and ask of the solution. Big picture of the path which we have to take forward is conceptualized in this part of the brain. Similarly, in the part D, part C, we have in the red portion, writing scenarios, effective communication of the plan, because effective communication to the others of, if we don't effectively communicate our plan to the others, it will not help us make any progress. If we communicate effectively, the progress will be more evident and more proper. Gaining belief, buy-in and enthusiasm, working through people issues. So you have to understand the perspective of the other people who are involved in your project and whom you are conveying your results and initiatives. Similarly, the focus on satisfying and serving customers and also tie into the values of the organization. So you have to train for the new skills and understand how you can bring change and accept the change, and make the people around you also to accept the change, so that you can progress well, and you can progress and lead your projects and the organization as well. There are some team ready for action assessment. I think this is more details. This is not the right time to discuss this. So the second solution is the SCARF model for brain and leadership, where the social brain first brings us the social pain of accepting the change. You have to accept the change, then only you will be able to go through the change. So it gives us a social brain. Social brain networks have to be oriented. We have to convey to our people how to how this change is helpful to us and why should we change. And then we have to mirror this in our neurons and make our brain work in that direction. So the SCARF model says here is a model of the social threats and rewards. If your change is, or the idea is accepted by the society, you will get the reward. Otherwise, society will think that it is a threat to us, and they will not accept it, and they will reject not only the idea but the individual projecting the idea as well. So when we are away from the threat response, and when you are towards it, or then you get the rewards. So status, we have to check the status at each stage, certainty of our ideas and the data, and the autonomy of the people around us, and our own autonomy, relatedness of the idea to the people, to the organization, to the society, and to the country, and its fairness as well. So there are some implications for the leadership. You have to make the employees feel better. You have to make the people or the scientists around you feel better about themselves, and provide a positive feedback on the status of your idea and its working. Provide clear expectations and give them ongoing feedback on their work. Avoid micromanaging. Give them some freedom and allow the people to make their own decisions in terms of the autonomy. Spend time building the trust. Discuss with them, and also bring in the relationship or relatedness, how they are related to the idea and how idea is related to them, both the sides. So be transparent and open to communications with them. Be fair and become effective coaches for them, to guide them. This will help us to guide the students, to guide the research work, and to guide the our individual groups, and in the end our organization and the country. So there are other solutions also, where the brain can lead to leadership. The characteristics of effective organizations include the adaptability, the efficiency, the flexibility. The adaptability is by becoming proactive, understand the idea and convey it to the others before the event, before taking any action. Then efficiency is while working, bring the whole work into the routine, and flexibility is not to react but to emphasize it positively. So simplicity process of the whole thing is here, the solution implementation or the project implementation, and the problem formulation, and the solution formulation. There are three components of it. We start with the problem finding. First we define the problem, then fact finding. We search the data around, search the literature, research on it. Then we define the problem, where the problem is, where the work is not done, and where the society needs some input, some more work to be done, to be helpful to them in different ways. Then we have to find the, after the problem is defined, we have to find the ideas to solve this problem. That is at number 4 here. And evaluate and select how these ideas are and will they work. Then we have to plan for implementation of the ideas. This comes under the solution implementation. Acceptance of the idea, it's acceptance of the plan by the people who have to work on it, and then finally take the action to bring the simplicity in the process. So in all, if we see, leadership is a process of change management, and a change management process should include employee or the focus group, focus more attention on cultivating moments of insight, communicate in a transparent manner the need of the change, ensure that the management keeps employees focused. So you have to keep them focused and not to deviate also. Give your staff, your people, your students, your scientists real power to implement their solution. Give them autonomy, suggest them solution, but give them autonomy to work out the solutions, to work out the benchwork, and to work out the results. And use both intrinsic and extrinsic incentives to change. What will be the, you have to tell them and indicate to them what will be the benefit they will be getting out of it. So there is a Covey's view of the trust. Strategy into execution into trust gives us the results. There is any of these three factors is missing, results will not be positive. So trust is looks like this. Can you see what this person is doing? Keeping the eyes closed with your hands and believe. That is the trust. So in summary, we can say to overcome the challenges associated with implementing the projects or the plans, to become a whole brain thinker, become a staff model acceptor, anticipate change before it happens, be proactive, use the best change management practices, and build trust. Because trust is everything which will make you successful or which will make you failure. So that is all for today. Any further information you can mail me. I will be able to tell you more information on this. And so the brain leads to leadership, and today we have learned how to maximize our teams or our real potential. So are you ready for the experiment?
Are you ready? Somebody has pieces of paper.
Now, how do I bring
I
myself?
think
How do I bring
maybe
myself into picture?
we cannot see you, and
That is because without seeing me, you will not be able to experiment. Not be able to see the hole in your hand.
yeah.
Uh,
So maybe we can do this in a later time because I think that's a bit of a problem. Our IT guys are not around. We are hitting the lunch time. So, but I would like to ask the audience if there is any questions for Dr. Wadhwa. I think the talk was very interesting. It forces us to think about a lot of
Anyway,
important issues.
anyway, I can verbally tell the experiment, and all of them who have collected a sheet of paper can do it.
Okay,
Please
we
roll,
can try. We can try that. We can try
yeah.
that.
Please roll the sheet of papers.
Can
Can you all roll the sheet of paper
I see
uh,
some people already rolling.
so that a finger can just go into it? Okay. Next, you keep this on one eye and see through the one eye through this. Keep your hand where the paper is ending, just close to that 1 inch before that. You keep your hand in front of the second eye. So through one eye you are seeing the through the paper. Second eye you are seeing through the hand. What do you see? See at the stage in front of you. What do you see? Can anybody tell?
Can anybody tell?
Sir, you can also experiment. You can show on the stage. I am able to see the stage.
There's a hole in the hand. There's
Yeah.
a hole in the hand.
Can you see it?
I think yes. Somebody already responded. Yes.
Can all of you see the hole in your hand?
Yes. Yes.
So this is how our brain works. There is no hole in your hand actually, but you can see the hole in your hand. Okay, thank you very much.
Thank you. Thank you.
Go home
Thank
and
you, sir.
experiment this with your children, and they will also enjoy.
Yeah. I think okay. So there are no questions, it seems, but I think people are really still figuring out how to see the hole or where the hole comes from. It's pretty
Thank you.
interesting. Okay. Thank you so much.
Welcome, sir.
Okay, so we break for lunch now. So we will resume exactly after 1 hour, and we will continue with the talks, starting with Dr. Nivedita, and then Nandini and Pragati. So, and we will do the discussion at the end of everybody's talks, because the discussion was very informative for the over the course of this meeting. So we will have a discussion session in the end of everybody's talk. Oh, okay. That's okay. Whoever is left, we will have the discussion with them. Yeah.
So I hope you enjoyed the last experiment in the lecture.
Yes, yes, yes. I think everybody is still perplexed of where the whole is coming from. Thank you so much.
Hope they will able to understand their brain well after this one experiment. Next time I'll give you another 1 or 2 more experiments.
Okay. Thank you.
Welcome, sir. And thanks for inviting me to this. Thanks to NBRC. Thanks to all the people who are organizing. Thank you.
Thank you for your support. Thank you for your support. Yeah.
Welcome, sir.
Okay. We break now.
Yeah,
Thank
sure.
you again. Okay. Okay. Bye.
Hello, everyone. So let's begin the next session. So we have Dr. Nivedita from IT Bombay for this session. She'll be talking on neural basis of sense of agency. Nivedita, over to you.
Yes. Do you hear me? Yeah. Yeah. Okay. Sure. Okay. Good afternoon, and thanks for staying back after lunch for the talk. So thank you, organizers. Always nice to be back here. It's like coming back home, see familiar faces. So today I will talk on the neural basis of sense of agency. So this is a project we've been working on last couple of years in the lab, one of the projects. And I'm sure many students will be familiar because they were participants in the experiment. So we have some data that we've tried to interpret with writing up, putting things together, and any comments, suggestions are most welcome. Okay. So I'll start off by defining sense of agency for those who are not familiar. So philosophically, if I have to say, it is basically what is left over if I subtract the fact that my arm goes up from the fact that I raise my arm. So which means if I have to put it in more scientific terms, so the subjective experience of controlling one's own actions and through them, the events in the outside world. So when I do an action, I am aware that the action has been made by me, and therefore whatever comes out of the action, the effect of that action, I am responsible for the effect of that action. So this is basically the feeling or the subjective experience is called sense of agency. So as you can see, it's a very subjective experience, and therefore to measure this and kind of see or infer anything, the neuroscientific basis of this, what exactly the brain is doing and how exactly this whole experience is generated is a challenge. And we actually experience this almost in everything that we do in our daily lives, say turning on the light switch or say doing any kind of voluntary action, and then even when we use your mobile phones, right? So when you like something, then it means that you are doing it out of your own volition. So the agency is kind of implied there. So association between the action and outcome is therefore key for the generation of sense of agency. You need to feel that the action that you did and the outcome that has come out of it, they are very closely linked. So to establish this association is what is crucial for generation of sense of agency. So there have been a couple of models that try to explain how the sense of agency is generated. So the more popular one is the comparator model. So wherein you start off with an intention or a goal. Say I want to switch on the light. So what if I intend, this is the intention that I have, and once I have that intention to switch on the light, then my brain is kind of planning as to how to do it. Right. So which means either I go and switch it on my right hand or with my left hand, or maybe I ask somebody else to go and switch it on. So how to plan this action is what is the first thing that your brain does, which is action selection. And once this plan is finalized, then it generates a motor command to carry out that action. And once this action has happened, then there is some change in the environment, like the light turns on. And now you have feedback both from the action from within your body and also from the environment, that you see the light on, fed back into your brain. So this is your sensory feedback that goes back into the brain. And there is a comparison that your brain makes with a predicted outcome. So once this motor command is generated, there is a copy of this motor command that actually goes back into a different region of your brain. And now your brain compares the predicted outcome with the actual outcome that has happened. And if they all match, if the predicted outcome and the actual outcome match, then you feel that you have been the agent of that particular action. So you feel responsible for the outcome of that action. So if I go there, but I don't switch on the light, but the light turns on by itself, then you do not feel that you did something, you did not do anything, but the light is on. So that sense of agency is not there, right? So very clearly, there are actually two two important components of this. So there is this prediction component, and which happens even before the action has taken place, and then you have this sensory feedback and sensory inputs that are going back, which happens after the action has taken place. So you have essentially a prospective component and a retrospective component that is necessary for the generation of the final phenomenon of sense of agency, right? So people have looked at this. This is, I think, last couple of decades is what people have been working on this, and they've used MRI and brain stimulation methods to identify which brain regions are actually responsible for this sense of agency. And they, as usual, they come up with a bunch of areas, but nobody knows how these areas are interconnected or are they coordinating with each other. And they also don't know what role each of these brain regions play in the generation of sense of agency. So that is still not known. So this actually started off. So how do you measure sense of agency, first of all? So they started off with a very famous Libet's experiment. So what it's based on chronometry, basically measuring the perception of time in your mentally, that is in your brain. So how you basically perceive time or measure time based on your perception, I would just say that. But I think when we talk about the experiment, you will know. So what actually the participants are shown is basically a clock face with a hand that keeps rotating at a certain rate. And then what the participants are asked is just to make a voluntary press of a key whenever they feel like pressing a button on the keyboard. They just press the button, and what they have to report is the approximate, that is the position of this clock hand when they had the intention to make the movement, when they had the intention to press. So this, and they recorded EEG during this task. And when they looked at the EEG over the central electrodes, what they found was, so this is time, 0 is the time point where they actually made the movement. And what was noticed was always when they reported the awareness of the urge to move, that is when they felt the intention to make the movement, this was always about 200 milliseconds even before the onset of the movement. And then they recorded this potential, this slow potential that that is called the readiness potential. RP is the readiness potential, which means that this is actually showing the movement planning phase. So the movement is actually, planning is happening more than half a second ahead of making the movement, and you are made aware of the movement only 200 milliseconds before the movement onset. So this is what was reported by Libet. And how does this relate to sense of agency? So Patrick Haggard from UCL. So what they kind of tweaked this experiment to add an extra component to it. So the same thing happens. The participant is sitting looking at this clock face. The hand is rotating. They're asked to make a voluntary key press. And some of these trials will also have will have a tone that is coupled to the key press, that is at 250 milliseconds delay. So some of the blocks will have a tone, an action coupled with a tone. Some of the blocks will have just the tone, and some of the blocks will have just the key press. And they are supposed to either report, depending on which block they're doing, they're supposed to report the estimated time when they actually saw, heard the tone, or when they thought they made the action in each of these blocks, right? So in that case, what happens? So this is only a tone only block. There is a tone occurring at some point of time, and when they asked to report the tone, there is awareness of the tone happens slightly earlier than actually when the tone was given. Now, when you look at the action and tone coupled together, this awareness of tone actually happens. Awareness of tone actually happens much earlier than it happened when there was no action that was happening. So there is a perceptual shift of the awareness of tone that is happening here. Now for the action only blocks, so again they make the action, which is the button press, and when there is no tone that is accompanied, they are made aware of the action just slightly after the movement. So this is not intention to move, this is just the awareness of them making the action when they actually made the action. So if you couple it with the tone, of course, what happens is there is shifted awareness of action. So they feel that they've made the movement much later than they actually did. And when we couple both together, they hear a tone much earlier than the tone actually appeared. And there is, So they would, I will show you the experiment. So they were, in the earlier experiment, they reported the time orally, verbally, but we actually tell them where exactly the position of the needle was when they thought they made the button press. So this is called temporal binding, or what Patrick Haggard started calling this was intentional binding. So there is temporal binding of the action and the outcome that happens, and more closer these two were, the more control they felt of the movement. So if they are more linked, so when you give a very predictable, so highly predictable outcome, then they think that they are more in control of the outcome of the action than when it very randomly happens, right? But what happens if this is only for voluntary movement? What happens if the movement is involuntary, like in the case of brain stimulation? So you give a TMS pulse, a magnetic stimulation pulse over the motor cortex, basically that controls the finger movement, the same kind of movement. You elicit a movement, but now this is not a voluntary action. In that case, they found that this temporal binding was not happening, but then the awareness was much earlier than of the action, and the tone happened, awareness of the tone was much later. So this kind of equated to an implicit measure of sense of agency. So as I said, there are two components, prospective and retrospective. And now, so this again paradigm was again modified or adapted to identify what are the prospective. If you can actually identify what component of this task can get you the prospective component and the retrospective component. So the prospective component is basically prediction, how well you can predict the outcome from the action that you make, and that will increase if the outcome is more predictable. So if you make the trials, say 75% of the trials have a tone and 25% don't have a tone, you have a higher chance of getting an outcome from the action that you made, as opposed to say a 50-50 chance of getting the tone. So here your outcome is not as predictable. This is completely almost random. And so when you compare a tone that a block where you get, or the trials where you get a feedback, that is a tone, compared to a trial where you don't get the feedback, that would give you a retrospective component. Whereas in the blocks, when you compare the higher probability of outcome occurring, trials with a higher probability of outcome occurring with a random occurrence of outcome, you get the predictive component or the prospective component of sense of agency. So this was done in patients with schizophrenia and compared to what happens in healthy individuals. And it was found that in healthy individuals, there is a much larger predictive component as compared to a retrospective component. And the black bars here is schizophrenia patients. You see the predictive component is almost non-existent, and there is more retrospective component, which means to say that the patients, they wait for the outcome to happen and they kind of attribute the outcome to the action that they probably have never done. So even if the outcome is not a response, an effect of their action, they kind of attribute the outcome, whatever is happening, to their own action. So this is what was observed. And therefore, it is important to identify, okay, which are the brain regions which basically are involved in the predictive component and the retrospective components. So this is a project Teston Sanath. Most of you might recognize him. So the data collection for this study was done here about 2 years ago. So we recruited 25 healthy adult volunteers. Most of you are here. And we did the same paradigm which was et al. Did. That is looking at the different prospective and retrospective components. We had 5 blocks, 32 trials each. So 2 blocks with 75% trials had the tone, and 2 blocks with 50% of trials having the tone, and 1 baseline block where we did not have the tone. And here we were looking mainly at focusing more on the action binding than on the outcome binding. So we did not use, and the experiment was anyway too long, so we did not initially plan to look at the outcome binding. So we did not have the tone only trial. So we recorded 64-channel EEG, and we got the MRI and also digitized the electrode positions for source localization, and did the pre-processing and analysis with a brainstorm toolbox. So this is how the task looked like. So there is this clock face that you can see and a cursor that keeps rotating at a certain rate. The participant is asked to fixate on the cross in the center, and so these are, if it's not clear, these are alphabets. Instead of numbers, we have random alphabets in some order. So with the numbers, it was very difficult because our students are much more well informed than about the task. So they try to anticipate. So they will decide, okay, when the when the hand goes to position 5, then I will make a press. So you should not really anticipate the movement. You basically have to report when you make the movement. So we had some problems with that, and therefore we kind of changed the numbers to alphabets, random alphabets. So they would just report the position, the alphabet that was closest to the position of the cursor, that at the time they made the movement or the time when they heard the tone. So this was the paradigm. So behavioral results were not very encouraging, but the one thing, so what we found, so this is the different trial conditions that we had, and this is the judgment error. So this we calculated based on the actual time at which the movement happened, minus the perceived time, that is the time that they reported when they made the movement. And as you can see, this judgment error is negative, which means there is an action binding. So the perception is always happens later than they actually made the movement. So compared to the baseline block where there was no tone that was happening, only the action was happening, you see that the feedback conditions had much larger sense of the judgment error as compared to the no feedback trials. This is only a trend, but according to the paper, what we found was we were able to show that there is about 10 milliseconds of judgment error with the prospective component and almost 1 or 2 milliseconds, very less with respect to the retrospective component. Statistically, we only found a significant effect of feedback, but not block or no interaction of block and feedback. And as expected, when you have more prediction, more probability of getting a tone, which is the 75 feedback condition, that had the maximum action binding as compared to the baseline block. So the original Libet experiment did not have this tone. They only, the idea was completely, they were not, no. The 250 milliseconds was the difference, the time difference between the action and the tone. And they also saw about 60 milliseconds. So when I look at the raw data, it was almost the same. This was the tone binding was about 60 milliseconds before, and the action binding was about 15 to 16 milliseconds later. So then we looked at the EEG data. So first we looked at the averaged EEG data. So what we saw was, this is the 75 no feedback and 50 no feedback condition. You see a clear positive increase in the amplitude. That we really don't know what exactly this is, but this is kind of localized over the left superior temporal, left temporal, parieto-temporal region. But again, the problem again came when we were looking into the retrospective component, where we're looking at 50% feedback and 50% no feedback condition, which means the tone is happening, and we did not see any difference except after the 250 milliseconds. So the 250 milliseconds was exactly when the tone happened, but now we are not able to disentangle or dissociate the effect of the tone and the effect of, say, any retrospective sense of agency. So 0 is the time the movement was made. So this is movement was made, and then we epoch the data to minus 2.25 seconds to plus 1 second, but this is 500 milliseconds. So here, the button press was actually made at 0. So there seems to be some prediction that is happening here, the predictive component that is actually happening here in the left parieto-temporal region. Although literature usually says the right temporoparietal junction, we actually will show you that. So the right temporoparietal junction is more relevant to this. So essentially, we are not able to interpret the 50% no feedback and feedback conditions, that is the retrospective component, because the auditory stimulus effect is exactly overlapping in this time window, and we didn't see any effect before that. So this was the ERP data, that is the averaged data. So you just basically put all the trials together and then average them within each condition. So then we looked at the time frequency analysis. So Rajat did most of the source localization. So here, yeah. So now when we looked at the time frequency data, so this is what we see. So this, it's not very clear, but this line, that faint line that you see, is the time of onset of movement, that is movement onset. And then what you see, so we've actually just looked at the data from 2 Hertz to 45 Hertz. And this is, the scale is from minus point, I think this is minus 0.5, no, minus 2, minus point, yeah, this is -2 to this one is plus 0.5. So 500 milliseconds here. Yeah. So what we see is, so this is again for the prospective. So this is for the 75 no feedback condition. This is what look like. 50 no feedback condition. This is what it looked like. And now the difference between the 75 and 50, which is basically the prospective sense of agency, what we see is a slight increase in the beta and gamma power just before the onset of movement, before they made the movement. And this was mainly over the, say, the frontal, midline frontal and the left central electrodes. That is your motor, sensory motor region here. They are, yeah, they are normalized to the data. Yeah, the baseline is from -1 to -2.25 here, because there is something that is happening here until -1. The threading when we see. So we did not want to use the data from 0. So the baseline was from -1 to -2.5, 2.25. No, same. In the sense, no. In the same, so each one had their its own baseline, normalized to its own baseline. Yeah. So now when looked into the source data, so what we see was there is midline, say around the SMA and also bilateral sensory motor region. We saw this this beta power. So here, don't get carried away by the color code. This is data for source localization. We just need absolute values. So the color code does not really matter, but it's just the localization. Just look at the regions where this actually translates to in the source space. So it's sensory motor region and say the SMA region for the beta and gamma initially, and then what you see is also on the paracentral lobules and a little bit overflowing into the cingulate gyrus. This is what we see. So it's basically the relatively higher frequencies that we actually see that there is some change that is happening, especially over the central regions. DSP standard, standard range. Yes, so it's basically the desynchronization is less. I don't know if it is. So there is. So this desynchronization here, I really don't know what this is causing this desynchronization here. We thought it would be because of movement planning, because in movement planning you do expect a beta desynchronization that during the movement, just before and during the movement, and after the movement you expect there will be a beta rebound. I thought this was something related to the beta desynchronization that is part of the motor, that is movement planning and movement execution. But when you take the difference, but if that is the case, it should be seen here also. But when it's more predictable, this one goes away. So this is what we saw in the pre-movement phase. So just after movement, this is what we see. So in the first 250 milliseconds after movement, you see most of the beta is still in the central region. Little bit of alpha that appears in the temporoparietal. This is time on the right side. And as it progresses, again, what you see is in the 250 to 500 milliseconds, you still see this beta has completely moved on, more alpha and beta that is moving on to the right temporoparietal region. So yeah, the same thing, what we did, but the time window is different. So again, prospective sense of agency, this is before, that is pre-movement time period that we used, and here it is post movement time period. This is the first 250 milliseconds before the tone, but after the movement, and this is after the tone that has happened. So before the tone is still like more central, but after the outcome has occurred, the activity moves more to the right temporoparietal region. In the source space also, we could map it again to more the medial, central medial regions and to the right temporoparietal regions here, and also more in the cingulate cortex and the cingulate cortex and also the angular gyrus, is that region, the TPJ around that region is what we found. So, okay, fine. So you see oscillations, you see some ERPs, but what does it mean when it comes to behavior? So out of all these, we finally found behavioral correlation. That is, so here we plotted the error in judgment, judgment error, which means the action binding that we saw in the 75 no feedback condition minus the action binding that we saw in the 50 no feedback condition. So which means here higher sense of agency means more negative. And on the x-axis, you have the gamma power, difference in the gamma power in the two conditions. And we see that there is a clear correlation. That is where there is higher prospective sense of agency correlates positively with the gamma power in the post-movement period, not in the predictive, but only in the post-movement period. This is what we see. So this is again immediately after movement. This is after the tone has appeared. So this is with the prospective. Now with the retrospective components, we did not see anything before movement. What we saw was immediately after movement, we did see some again activity in the central region, but now it is all more in the lower frequencies, the delta and theta bands. We don't see anything in the beta or gamma here for the retrospective component. And this again, this is after 250 milliseconds when the tone has occurred, which cannot be really interpreted because of the auditory component that you will have here. Right. So, and this, so initially this is the central, and then once the tone comes in, then you see activity all over the place and you have bilateral temporoparietal activation. So now we are doing control, like retrospectively, now we are doing control experiments to just look at the effect of the tone alone and looking at the tone binding. So this maps onto again the source on the source level. Here mainly area that you see is the main area that you see is again the temporoparietal junction, right temporoparietal junction, and again it is theta and delta, low frequencies. Oops. Yeah. So so to summarize till now, so the sense of agency is the subjective experience of feeling in control of one's action and therefore its outcomes. Implicit measure of sense of agency is intentional binding, and this is not an ideal or the gold standard paradigm, but this is the best that we have till now. And it is possible to disentangle the prospective and retrospective components. With EEG, we have identified some correlates which could possibly be related to each of these components of sense of agency. What we can infer till now is that the power of higher frequencies, more beta and gamma, is correlated positively with the prospective sense of agency. But I will hold back and not really comment anything about the. So this shifts over again to the right parietal temporal regions. With the retrospective agency, sense of agency, I will still hold back and not really infer anything at this point, but looks like most lower components, the lower frequency bands seem to be important for the retrospective component. And so we want to look at, next is to look at the causal association of these neurophysiological correlates. So what we are currently doing is we are running experiments by stimulating these two regions, the right TPJ and the SMA region, to look at differentially the effect of these TMS, transcranial magnetic stimulation, on each of these components of sense of agency. And if we would get something out of it, say a certain frequency band that it seems to be important, then we want to, in the long run, kind of try to modulate it with non-invasive methods. I would not just say stimulation, but maybe even neurofeedback training. So coming to societal importance, so clinical relevance of sense of agency in patients is also more than we think they are. So in patients with functional movement disorders, where they have these abnormal movements like tremor and say abnormal gait and so on, but what happens, wait until I finish, then you take picture fully. And so what exactly happens is as when you examine them, do the investigations, you can see the clear readiness potential and voluntariness of the action of their movement, abnormal tremor, but they feel that they are not making it. It is completely involuntary. So they lose that sense of agency on their movements, abnormal movements that they have. And this was previously called psychogenic movement disorder, but this is a big, good, at least 10% of patients who come to the clinic with movement disorders present with functional movement disorders. And schizophrenia, especially, as I told you, they anyway have abnormal sense of agency, not just with action, but with thoughts. So they cannot distinguish well between thoughts that are internally generated as opposed to talk that are induced externally. So that is one thing. And then when we talk about so what happens, what we know is coercion, coercive instruction like in the military reduces the feeling of sense of agency for bad outcomes. Could be between your guy and you, but this is a much more, I don't even have to debate about this. So coercion decreases the sense of agency, and therefore it is possible, most likely the soldiers, they claim that, okay, I was told to do this and I did not do it by myself. So they claim I'm not responsible for bad outcomes. So this is one place where you want to look at sense of agency. And in the court of law, you're looking for criminal liability, you're looking for an intention to do a forbidden act. So which means the crime, there has to be an intention to commit a crime. And their sense of agency is very crucial. And with advancements in technology, even if you're a drone pilot, okay, how do you define whether you were the agent of, are you responsible for the actions that you have made? So it could be a neuroprosthetic level. So you have a prosthetic arm, but when you use the arm, do you think that you have made the movement? So is it your, is the agency implied? You basically have to learn the agency. So it's important in many dimensions. So yes, finally, my lab with humble beginnings from NBRC. This is where we are now after 3 years. And with 2 additional postdocs now just joining the team, they will be working on eye movements in PD, funding, and my collaborators. Thank you.
The Libet's experiment, there is you have to report about when you made the decision. So it is natural to have these 2 times to be different.
Yes.
But in this case, you are supposed to know when you pressed. So there is supposed to be a congruency there rather than supposed to be a difference for the subject. Correct. So I am puzzled by that aspect.
Yes,
when
so the time point, yeah, we think it's all instantaneous, but there is obviously a delay between you making the actual movement and you being made aware of that movement, and that is the delay. It's always after the movement. Yes, so it is after. When they made the movement, it is after they have made the movement. Oh, so in that, so once they've made the movement, then that screen goes off, and then they have this clock face coming up, and they have to press the letter where exactly they thought they made the movement was, exactly the position. So it's completely after the 1 minute, 1 second that we have this on the face. So they don't do it. The clock face, the hand on the clock, the cursor keeps moving for at least half a second after they have made the movement. So here.
So did you look at the ERPs for that slower, that delta theta condition where you see low frequency?
So in those regions, so this is completely data driven. So which means if we have seen some ERP, so this was the initial ERP analysis did not give us anything that is, so this was so completely data driven. So we did not have any hypothesis. So we put in all the 64 channel data, and this is what actually came out significant based on the cluster based permutation analysis. So, and this ERP is plotted from this set of electrodes. So we did not really plot it from the central electrodes, which would be exactly the readiness potential. We did not see significant difference in the readiness potential as such in the central electrodes. So basically the preparation movement planning was similar in all conditions. This is something extra that is happening here during prediction, that is happening in the left parieto-temporal region.
Okay,
but
so the
I didn't
reason
understand why. So
well, yeah, I'll tell you. The reason is that when you see some sort of an evoked response, it reflects in the time frequency spectrum at low frequencies. A Gaussian, for example, if you resolve it, it will have. It also is a Gaussian in the frequency domain. So a lot of this low frequency stuff that you tend to see and see, say it's alpha, theta, delta, it's actually just some sort of an evoked response. So it's always a good idea. So in the next one, to just check whether the evoked response is changing, and then you can in fact subtract it off and see if it's there in the induced response.
Yes.
That's why I was asking.
Yeah. Okay. This one. So the thing is, again, we have to do this. No, the next one. So this portion you're telling, right? This one is the low frequency. Yeah. So that's why I cannot, we are not even trying to interpret anything from here. As of now, because there will be an evoked response because of the auditory evoked potential. They hear a tone exactly at that time. So around like 300 milliseconds, we do expect an auditory evoked potential there. So it could be well because of that as well. Huh. Okay. Hmm. But that did not come up, but this did not come up to be significantly different. The difference was only here. Okay, here in the previous one. Here. So, but this was not really this was not significantly different. The only main thing that came up was beta and gamma. So here only this band, but the low frequency did not withstand. It is more prominent, but unfortunately it did not actually show up. So when you do the multiple comparisons, this does not withstand. So 2 to 45 hertz. 2 to 45 hertz. So this is still around in the alpha, but it was just, this itself is yeah, this is theta. Yeah, this is theta. No, this is plotted on. So here, so higher probability is 75% no feedback minus the 50% no feedback, which is basically the prospective component, the predictive component. Comparing this number to, so they were comparing these two, and this is what we get. Yes, so there is, so okay, that you mean. So here there is, so here we are comparing it to the baseline before any activity started. So the baseline here is 1 second before they made the movement. Significantly different is difference between these two conditions.
Yeah, so you are doing a test of the number on the third graph against 0, right?
So the statistics is run between this and this, condition 1 and condition 2, assuming that this difference, the null hypothesis, it is 0. This one is 0. Yes. So the entire band and all electrodes. So they have this cluster-based permutation analysis. Yes. So every electrode and every time point and every frequency. So it does not withstand this multiple comparisons. So we because the dimension is like really big. So 64 by say a number of time points here, I think it's about 1000 hertz. So it is about 1000 points, and say 2 to 45, so 43. So the dimension is huge. So it will not withstand so many comparisons. It's probably that's what it is, but it did not show up at all. No, the ERP with so with the source. It's DSPM, which is the standard in the brainstorm tools. DSPM, statistical parametric mapping. So here, what they claim is because if you use individual, when you do this, map it on individual MRIs, then the sign here actually would matter. The direction would matter. But now because you're putting all of them together in one pool and kind of normalizing everything to the template, then you cannot really infer anything from this. So that is why this is positive and this is like negative. Yeah, I get that. We'll check that. Yeah, yeah. I get that. Yes. The low frequency. Got it. Okay.
All right, no more questions. Let us thank Nivedita for the interesting talk. Okay, so the next talk is by Professor Nandini. Uh, she comes from UNESCO MGIP, and she doesn't need any introduction to all, I guess, right? So, over to you.
It's a pleasure to be back as always. Like I was telling a few of you at lunch, my family said this morning that Nandini is going back to Jamaica. Okay, they're coming back to NBRC. So thank you very much for thinking of me at such an important juncture. This is NBRC celebrating 25 years, and I'm still very emotional about that place. So before Prateek leaves, I just want him to know that the 500,000 people or half the planet getting together to watch football is because of emotion. So, so if you had stayed back, you would have learned why, but maybe I can come to Gandhinagar and tell you about it. Okay. So I'm trying to probably fill in a little bit of the behavioral or the societal impact of what some neuroscience work is now starting to tell, primarily in the context of education. Something that is now largely comes under a banner of educational neuroscience. And given the fact that humans are social emotional beings and how much of the cortex is devoted to being social, it's surprising that we don't study this more. I think we're starting to look at this much more in detail. So I think we are all aware that we have a big mental health crisis on our hands. And it's a little sad and worrisome that a lot of it is happening amongst the younger age groups. Okay, so on the right you see data from a WHO study, which showed the horrifically large numbers of children who are facing stress, anxiety, loneliness, and a big disconnect from parents. These are the numbers worldwide. Okay? And as a consequence, a point that is beginning to worry policymakers world around, and of course parents and all of us too, is the fact that there seems to be a big breakdown in building relationships. So what can we begin to do in terms of trying to address this on a societal level is something that organizations like the UN are now beginning to consider. In short, human well-being seems to be at a huge risk, and some of it came about during the COVID crisis also, when we were sort of shut down or shut up in our homes. A lot of what we see around societal structure is, especially in the context of education in, say, quit or I'm talking more about the under university students also, is compromised physical health, first sleep quality, bullying, which is at an alarming increase, and stress and anxiety in the classroom for various reasons. It could be competition, it could be lack of acceptance from peers, it could be because of breakdown of communication with parents. But all of these become quite rampant in society, and it's not urban or rural. It's all over the place and it's all over the world. But what a lot of research, very detailed research like the kinds that's been talked about earlier, has now established for the first time that well-being can actually be trained. Just like you teach children to read, you can actually teach them skills that are responsible for them to promote and foster their own well-being, okay? Which is essentially neuroplasticity at play again. Okay? And therefore, the fact that well-being is malleable has been an extremely influential idea in the last 10 years or so. And this can actually be cultivated through intentional mental training. which is why I was very interested even in the previous talk to begin to see this whole notion of intention, how it can be looked at even in these contexts too. So when do we begin to be intent on trying to ensure our own well-being? So a lot of people like Richie Davidson being one of them has been playing a very important role in trying to bring about this idea more strongly in all of learning situations also. Okay. A lot of this is believed to and is now fairly well established to arise out of training the social and the emotional brain. And in short, social and emotional learning is now being described as the ability to cultivate knowledge, attitudes, and awareness to recognize and manage emotions, develop care and concern for others, establish positive relationships, decision making, and resolve conflict. I think we all are completely aware of the fact about how much conflict we have to encounter on a daily basis. It can be contexts of different kinds. Decision making, if somebody paused to ask you, you'll be surprised to know that most of us make close to 30,000 decisions in a day, starting from what you want to wear to what you want to eat, to whether you should listen to what's being said in class or not, or whether you should get into a fight or not. Okay? So there's a lot of decision making happening. When the decision making is happening, there's both the rational and the emotional brain that are working together to be able to make these decisions. Okay? And so now there are a bunch of competencies that people have shown can be explicitly trained, okay, in order towards building these social emotional skills. So just like in classrooms, you teach children to do numbers, to learn to read. Now there is an attempt being made to actually build these competencies in classrooms too. And that's a lot of what my work now revolves around, in how to study these and how to build paradigms as well as educational programs where these can actually be mainstreamed into classrooms. Okay. So just to give you the background for what's the proof that this is actually malleable, I'm just showing you one such study which has been quite remarkable. This has come from Tanya Singh's lab, another person who's done a lot of very influential work in the field of social and emotional learning. She's one of the first people who studied the neural correlates of pain, okay, and how when people feel emotional pain, the same regions of the brain that are activated even during physical pain actually show up. Okay. So Tanya studied, and I'm going to sort of rush through this a little bit because there's a lot to talk about. Actually went through a mental training program with individuals. This is for older people that lasted over 9 months, where they were provided explicit training for which was able to show very well how there were structural changes in the cortex in both temporal and frontal areas, as well as functional changes that were seen. And this has led to about at least another 500 studies that have now shown that you do see structural and functional changes in the brain following these explicit training. So outcomes of some of these social emotional trainings are listed out here. Reduced burnout, improved academic performance, healthier relationships are three that I think we should all focus on, because these clearly improve quality of life and well-being directly. Okay. Yeah. So this is generic, but this is based on the training that they go through. So this is the training. So there's a fairly intensive training program. I will talk about some aspects of it as I go along. So they've actually been able to show that there are actually changes at the level of lengths of telomeres too, people who go through this training over an extended period of time. It's worked by Clifford Saran from UC Davis. But I think at MGIP, the role that we are trying to sort of change some of the conversation in education is, a lot of education right now is essentially designed to look at content and assessment, primarily to teachers, but to ensure capabilities for economic growth. Okay, so that's how the human capital is looked at. But what if we could change the whole basis of education to have this as only one of the components, but to ensure more human flourishing so that people are able to recognize and grow their full potential and achieve that as an outcome. Okay. So how can human flourishing be a better driver, which as a consequence could probably lead to lesser conflict, both at the global level as well as at the individual level. Okay. So around the time when I joined MGIP, we wanted to come up with a framework on what are the kinds of social emotional skills we want to build. And we looked at four, which now conveniently came onto the EMC square framework. So we looked at cultivating empathy, mindfulness, compassion, and critical inquiry. And these are some detailed competencies that one would actually want to cultivate in children. Okay. But why would we want to look at these four and how might they be related to well-being is something that you might want to question. Okay. Now, empathy is something that we are all born with. Okay. Over a period of time, we somehow don't nurture that enough. And there are two aspects of empathy. One is cognitive empathy, which is the deliberate process of perspective taking. So you understand the emotional state. And the second is affective empathy, which is actually getting involved in that emotional state. A lot of affective empathy can lead to empathic distress and not enough action. Okay. But cognitive empathy does still enable you to take action to change things. So empathy has now been established reasonably strongly to impact well-being in a strong way. Okay. Mindfulness came a lot out of a very influential study done in 2010 by Klingsworth, okay, who sampled about 10,000 students in the United States and asked them just three questions. What are you doing now? Where is your mind right now? Is it focused on what you're doing or is it focused elsewhere? And how unhappy or happy are you? And what they found was that 47% of most waking people are not paying attention to what they are doing and are consequently unhappy. Okay. So a wandering mind is an unhappy mind. And so it's important to be able to cultivate and train attention to be able to actually be focused and end up just improving your own well-being. Okay. So now there's, again, very good research to show that mindfulness training actually reduces mind wandering. And for me, a definition of mindfulness that has worked is just the ability to know at any given point in time, if you know what your mind is thinking about. I can assure you out of the maybe 40 people or 30 people sitting in this room, at least 25 are mind wandering. Okay. And you can ask yourself that. Okay. But we now know that conscious training in this actually does help. This is, yeah, sure. So the well, a lot finally boils down to how much of that time do you end up doing that. So if you're sitting in class and if your mind is wandering a lot, you're probably not going to end up understanding or taking what class is supposed to be doing. Right. Yes, when you're sitting around and doing nothing, mind wandering is encouraged. It's the basis of creativity. That distinction was not there in that study. Yeah, but a conscious effect that people are bringing into the fact is if you're wandering a lot more, especially when you're in class or when you're focused. So do you actually end up achieving goals? Hmm. So that's why the cause for bringing this into classroom level so that when teachers are actually doing classes for about 45 minutes or 50 minutes, if they are able to bring in practices at periodic levels to ensure that students are engaged in the classroom, will ensure better transfer of information from teacher to student. That study was just one of the indications of why mindfulness is important. Okay. So this was the results of one short mindfulness training that was done at a classroom level, again using online mindfulness training, which showed improvement in resilience, changes in stress, improvements in positive mood, and changes in negative mood. Okay, and this in turn led to improved well-being for students. Finally, compassion. Okay, something that has been largely undervalued. Okay, but is now emerging to the extent that there are even people in psychiatry who are beginning to recommend something like this on a daily basis to have a positive sense of well-being. So just like if you go to a cardiologist today and along with the medication that he or she might write for you, they will write 30 to 40 minutes of daily walking. Okay, there are psychiatrists who are now beginning to add regular effects of kindness is something, or pro-social behavior is something that you are encouraged to do. Okay, so familial compassion, it is compassion or kindness towards your friends. Yes, absolutely. Gratitude and pro-social behavior is also one of those competencies that's very much being encouraged. So to consciously find out time to do an act of gratitude on a daily basis is something that's being encouraged strongly. And there are schools now that are bringing it into their systems. Okay. But to also have a sense of global compassion, that is compassion even for people not directly connected with you, is being encouraged. Okay. So to be able to get to the chase quickly, you know, we came up with all these important competencies, but how do you try and cultivate them? Okay. And another aspect which a lot of neuroscience work is beginning to show is the whole change in the whole mode of teaching and learning is to make it more active. Okay. So we've had a lot of passive. Absolutely, absolutely. So there are very interesting studies amongst Israelis and Palestinians too, which have actually implemented these programs. Maybe we can talk about those separately. But one of the things we wanted to use is active gameplay that happens through digital games, okay, which a lot of youngsters regularly engage in, to see whether these can become avenues or narratives around which some of these ideas can start to be cultivated. Okay. Given the fact that we are all evolutionary wired to play, it becomes a convenient medium. Most importantly, it's a medium that youngsters are willing to engage in. Okay. So I'm going to talk to you very quickly about a short study we did where we actually took one such game. Okay. The game is called Bury Me My Love. It's a BAFTA game, so it won a number of big awards. And I'll let you just watch maybe a minute of the game to give you an idea how engaging it can be. This is a refugee camp, and this is a young girl who's escaping from Syria to Europe. And as a player in the game, you have to act as her husband or partner who keeps providing her instances on how to navigate going from Syria to Europe. As if you're going on text messages that you are passing to each other across mobile phones. So the entire game is essentially played in that format. So a game that lots of young people enjoy playing a lot and has a huge sort of interest across the world. So a lot of, or all the work that we do is all in the digital space, where it tries to make use of digital affordances that technology allows to also be able to address diversity in terms of learners in the way they want to learn and can learn. Okay. So we use the game as a narrative. It's like a story. And then you pause at specific points in the game to be able to create a course online. Okay. That course has activities built into it through which you actually learn about why people are migrating, um, what might they need at times when they are migrating. If you have such people in your surroundings, how do you think you can actually make them part of your homes or make them feel more welcome, and how important it is to be able to play these roles to be able to build a kinder empathetic world. So we actually get young people to examine and understand the notions of migration, belonging, and their own identity, then empathy and mindfulness, and in the context also talk about things like the Syrian refugee crisis. So we do something similar with the climate change game also, that teaches children about climate change, but also gets them to take action towards it. Okay? So this is how the game looks on the platform called Framerspace. And students, as they play the game, actually also document their experiences and their interactions through the game. Okay. So here are some examples of the kinds of questions that you are asked during the game. So think of this if vis-a-vis a teacher who was uh, in a history classroom talking about migration and just telling children about it, vis-a-vis playing something like this actually on a platform and what they take away. So we conducted a small research study around this game. Okay. So there's a pre-assessment, which I'll tell you about. Then there's gameplay. You actually go through the course, and then there's a post-assessment after the game. So in the assessment measures, we look at knowledge and attitudes in terms of migration, refugees, respect for other cultures, empathy, 2 scales of empathy, and 3 scales of compassion. Okay. And we did the study across 2 countries, India and the UAE, with about students in the age group of about 14 years or so, matched as far as possible as we could. After this entire process was over, we found certainly improvement in knowledge, okay, in terms of awareness and respect for people from other cultures. This is typically what your current classroom assessment system does. But because of the other competencies that we also looked at, one other interesting finding that we had was improvements in compassion from others, primarily in females. Okay. And one of the reasons we think we explained this was that the protagonist in the game is a woman. Okay. And probably the identification of what she needed and was going through, that level of empathy probably happens more strongly in female students vis-a-vis male students. Okay. And then when we looked at empathy compassion correlations, we found that practicing self-compassion, that is being compassionate towards yourself, actually enables you to also accept compassion from others. Now, if you look at the literature, one of the things you will notice is we often tend to be very hard on ourselves, especially with young people and adolescents in the age group of maybe say 12 to 18. Students and children, adolescents, young tend to evaluate themselves very harshly when compared with their peers. Similarly, we found that there were people who had an interest in learning about other cultures also showed an increased ability to be able to offer as well as receive compassion. And finally, the fact that self-compassion, remember I talked about cognitive empathy, people who had self-compassion correlated negatively with affective empathy. We saw a weak correlation with cognitive empathy, but a strong negative correlation with affective empathy. That is, they won't get involved to the extent that they will not be in a position to help. That's really the difference between sympathy and empathy. Empathy allows you to make a difference. Sympathy can often help you, enable you to get so caught up that you cannot take any action to improve the other person's state. Okay. And so we try to start building this into courses that are available on our platform called framerspace.com. And these are courses available for all of you to take. So there are courses for young people, there are courses for teachers, and there are courses for young students, which are coordinated through teachers. We are now making one through for decision makers so that they might be able to take decisions in more empathetic ways. What I do want to end with is for you to have a look at what this video says, which I might not have been able to say. Emotional contagion, right? Thank you. Any questions now or at the yeah.
So I guess you may get this question a lot, but so see, we try. So I have a 7.5-year-old son, and we basically try to limit his screen time a lot. It's a, it's an addictive thing, playing games and all that. You should actually interact with your friends. The usual stuff that you talk about. I know this literature on the effect of gaming, first person games, it can improve certain things and all that, but just to play a game, and it's basically you're saying things will improve, but isn't that also going to potentially lead to other issues with addiction with cell phones and things like that?
So your point's very valid, and yes, I get this question a lot. This is one of the things that we do to try and teach these skills. Okay, we also try and teach them through things in the classroom. But there is increasing work to show that digitals also allow a lot of active learning to happen, and that is probably the game changer that we're talking about. If we are doing passive gameplay, that's not helping. But active gameplay is doing certainly better than a passive teacher in the classroom. That there's very good evidence for. So it's how you engage with the digital medium. And if it's back and forth where you're learning, you're actually ending up learning much more versus sitting in a classroom where there are teachers talking. So one of the reasons we encourage kids to go out and play is, again, it's active exchange of information. So the critical role here is that active back and forth. So again, even young children who only hear things versus have active engagement show much better brain development. That's been well established. So it's that active exchange that a digital medium might allow in a specific format that's certainly showing very encouraging results versus passive downloading of information that might be happening in classrooms. So a lot will depend on how much of that video game that kid is playing and for how long. Policing is clearly important. I'm not saying that's not important, but digital affordances are also allowing us to find ways to teach all kinds of kids, because not all kids are learning, unfortunately, at the same pace. Yeah, I mean, you can do it for half an hour in a day, and if you're able to police it, then great. But this is just one example. But a lot of this is translating into real life, and that's something you want to encourage. Mm-hmm. Mm. Right. Content matters, engagement matters. Okay.
Hello.
Is this like one critical time or what, when everybody decides to sort of walk away? There's just like an efflux. I figured. No, please do. I was just wondering if there's something in the program I missed. Yeah, absolutely. Completely understand. Completely understand. Please, absolutely.
Hello, I have a question.
Sure.
So all of us have some uncomfortable points.
Yeah.
So have the children. Let's suppose you make a game for the children. How do you control for any uncomfortable triggers that might appear as stimulus on the game?
So a lot of effort and time is spent in making sure that you stay away from uncomfortable triggers within the game. And whilst gameplay happens, it's encouraged to be supervised so that support can be provided should triggers become available. So that's the training that we do with teachers when they are going to use these in their classrooms on what might be the triggers and how to manage them.
Okay, so it's done for every child individually.
It depends on how the school decides to incorporate it. Some of them actually want to do it in terms of actual interactions in the classroom. So they will show, for example, or a part of a game and then have a discussion in the classroom to begin to normalize it. But most classrooms don't even encourage discussions about what is a trigger and whether it gives rise to a change in emotion. We are trying to find a way to normalize that inside a classroom.
Okay, thank you.
Thank you so much, ma'am, for such an enlightening talk and actually working on this topic. It's really nice to hear this. Ma'am, what I wanted to know is that meditation is said to play a very important role, and it kinds of brings under in it a lot of the social emotional learning
Yes, absolutely.
components. So a lot of countries, specifically in Europe, like Denmark, has now made it mandatory in
Yes.
their program to include meditation at a younger age.
Yes.
So what do you think would be like how can this actually be translated and get implemented at like a national level, and like how can it, it benefit the society at
So
large?
the Delhi's Director of Education in Delhi actually has institutionalized this in all their schools, and we did a huge training with their teachers. And there is, even though it has started out in a very small measure, it has shown very big impacts in terms of student outcomes, in terms of academic performance, in terms of even engagement and improving teacher-student relationships. What has also helped in this whole process is the effort that they have spent in bringing parents into this conversation very actively. At, that model is now being actually studied by multiple governments, and if you go to a Delhi school, government school on a regular day, there will be some country or the other that's visiting. That's how popular it's become. But there are a number of schools in different parts of the world who have actually institutionalized these. And so now teachers in a classroom, for example, when they start out a classroom, there will be something called circle time when the people get together. Then at, somewhere in the middle of the classroom, there will be a pause. And students, really young kids, actually have already started to spend a little bit of time introspecting. So they start by just counting their breath, maybe 10 times. Teachers have, ends up as being a way to teach kids counting, as well as making them aware that there's a change of focus that begins to happen when you begin to focus on yourself. And so student outcomes are improving extensively in classrooms too. So it's happening in a very slow way, but it's beginning to happen. Okay, let me pause it. Thank you.
Thank you, Dr. Nandini. It was great, a great talk, tremendous talk. I have a request. Can I get that video, the one that you showed at the last? Yeah. All right. Thank you. Thank you so much. Okay. So now we